Welcome to Night Cosmos Sleep. Someday, human beings may step onto the moon or Mars and build the first living quarters in a world with no air to breathe. But reaching those places will only be the beginning. The real challenge will be finding a way to keep living when water cannot be wasted, food cannot simply be replaced, and a single broken device could threaten the entire base. To search for answers, NASA is preparing a group of volunteers to live in isolation for about a year in Houston. They will still be on Earth, but behind a sealed door, every breath, every cup of water, and every decision will be measured as though they were millions of kilometers from home. This experiment is not designed to create an adventure. It is meant to answer a question that sounds simple, yet is extraordinarily difficult. Can human beings turn a sealed room surrounded by a deadly environment into a place safe enough to call home? To understand why finding that answer requires an entire year, let us begin with the first morning after the door closes. The first morning inside the simulated habitat begins without a sunrise. The ceiling lights switch on at a scheduled hour, replacing the sunlight that would normally stream through the windows of an ordinary home. There is no sound of cars passing outside, no birds on the roof, and no noise from the city of Houston waking up. Inside the sealed environment, there is only the steady hum of ventilation fans and the small screens continuously displaying the status of the habitat. The temperature remains stable, the air continues to circulate, and the power system shows no signs of anything unusual. Everything appears quiet, clean, and so carefully controlled that there seems to be little cause for concern. But for the people waking inside the habitat, this is the first morning of a year in which they cannot simply open the door and step outside. From this moment on, every day of their lives will unfold within a space whose boundaries have already been set. They are still at Johnson Space Center in Houston, not on the moon or aboard a spacecraft traveling toward Mars. Only a few walls away, the sky is still blue, trees are still moving in the wind, and the roads are still filled with people. Hospitals, stores, restaurants, and ordinary homes still exist just outside. Yet, throughout the mission, these familiar parts of life will temporarily disappear from their daily world. NASA is not trying to convince the participants that they have truly left Earth. They know there is no vacuum surrounding the habitat and no distance of millions of kilometers separating them from their families. What must be simulated is not the view beyond the window, but the quiet pressure that begins to emerge when people must live through a long-duration mission. These pressures are small, repeated day after day, and gradually become heavier as time continues to pass. Their living space will be limited, their work schedules carefully organized, and every resource used according to plan. Food cannot be chosen freely, water cannot be used without thought, and the equipment inside the habitat will not always function perfectly. A task that seems simple may take longer than expected, while a single sleepless night may affect concentration throughout the following day. These difficulties may not seem serious when they happen only once, but they become something entirely different when they continue for months. More importantly, the same people will remain beside one another day after day. They will wake together, work together, share meals, and face every problem that arises inside a space they cannot leave whenever they choose. Each person will be a colleague, a neighbor, a dining companion, and someone responsible for supporting the rest of the crew when an unexpected situation occurs. The boundary between work and private life will almost disappear. The mission can be imagined as moving into a house in an extremely remote place, where there is no store at the end of the street, no nearby hospital, and no repair technician who can arrive after a phone call. Under those conditions, every problem must be handled by the crew themselves. If a device malfunctions, they must inspect each component, identify the cause, and repair it using only what is already available. If essential supplies are used too quickly, they cannot simply place an order and wait for a delivery the next day. Every decision must be made with the understanding that outside help is no longer easy to reach. Even small disagreements become more difficult to resolve inside a closed environment. On Earth, someone can step outside, take a walk, visit a cafe, or return to a private room until they feel calm again. Inside the simulated habitat, that distance does not exist. Only a few hours after an argument, two people may still need to sit beside each other to inspect a system, prepare a meal, or complete a task that requires precise cooperation. During the first few days, everything may still feel new and exciting. Every room offers something to explore, every device sparks curiosity, and every assignment reminds the participants that they are helping prepare for real journeys in the future. At this stage, a demanding schedule may provide a clear sense of purpose, while carefully planned meals have not yet become repetitive. The initial excitement helps people adapt more quickly to changes in their environment. But novelty cannot last for an entire year. After a few weeks, the corridors begin to feel familiar, and the screens inside the habitat no longer attract the same attention. After several months, meals begin to repeat, new stories become less frequent, and the sound of the ventilation fans becomes a constant presence in every moment. A schedule that once felt inspiring may gradually turn into a sequence of similar tasks repeated from one day to the next. This is why NASA needs a mission lasting about a year rather than only a few days or weeks. A short experiment can reveal whether the equipment works properly and how long people need to learn how to use it. But it cannot show what happens after the excitement has faded. When the body begins to grow tired, and when every crew member has become deeply familiar with the smallest habits of everyone else, many problems appear only after enough time has passed for them to accumulate quietly. Fatigue may arrive so slowly that the people experiencing it do not notice at first. The ability to concentrate may decline after weeks of shallow or insufficient sleep, while motivation can begin to change once the days ahead no longer carry the feeling of discovery. A small sound, a particular way of arranging objects, or a habit that seemed harmless at first may become increasingly difficult after being repeated hundreds of times. In such an environment, even the smallest details can influence mood and affect how well the entire group works together. At the same time, a long mission can also reveal how well human beings are able to adapt. One crew member may learn to create a sense of privacy with nothing more than a pair of headphones or a familiar corner to sit in. The group may develop small rituals, such as sharing meals, spending a few quiet minutes together at the end of the day, or dividing responsibilities in ways that better suit each person. These simple routines may help prevent life inside the habitat from becoming a series of days that feel completely identical. The mission is expected to begin no earlier than August 2027 and last for about 1 year at Johnson Space Center. Participants will live in 2 habitats isolated from the outside environment, with each one representing a different stage of the journey. NASA wants to observe not only how people endure life inside a sealed space, but also how they change as they move from traveling through space to working on the surface of another world. The Hera habitat is used to simulate the months-long journey between planets. Its interior is arranged like a crewed vehicle, where every area has a specific purpose and every square meter must be used carefully. Within this environment, the crew must live, work, exercise, rest, and handle unexpected problems within a very limited space. The feeling of confinement does not come from the room being small for a single day, but from the fact that it remains exactly the same after hundreds of days. The Chapia habitat serves as a surface base on the Moon or Mars. Here, the crew carries out the kinds of work they might perform after completing the journey and beginning life on another world. They may tend crops, prepare food, maintain equipment, conduct research, and manage limited resources. This environment allows NASA to observe how people transition from living inside a vehicle to living at a base that must operate reliably over an extended period. Combining the experiences of Hera and Chapia creates a broader mission than earlier simulations. NASA can follow how people adapt from the beginning of the journey, through months inside a confined space, into surface operations, and finally as they prepare for the trip home. Each stage creates a different kind of pressure, but none of them exists in isolation. Fatigue, accumulated during the first phase, may continue to affect performance during the next. The participants will also carry out simulated excursions outside the habitat and use rovers to travel to locations far from the main living area. Before each excursion, they must prepare their equipment, calculate the available time, check the resources they will need, and divide responsibilities among the crew. After returning, they continue by processing data, maintaining their tools, and checking whether any problems appeared during the operation. These activities help create a daily rhythm that more closely resembles a real exploration mission. Of course, they are not actually walking on the surface of the Moon or Mars. The excursions outside are only simulations, and the rover is still operating in an environment far safer than space. What NASA needs to observe, however, is how people prepare, coordinate, and make decisions when a task does not unfold as planned. If an excursion takes longer than expected, a piece of equipment malfunctions, or one crew member begins to grow tired, how will the group adjust? Throughout the mission, NASA will not simply count how many tasks are completed. Researchers will also monitor sleep, health, concentration, resource use, and the level of coordination among crew members. Someone may complete an assignment on time while still feeling exhausted, stressed, or gradually losing motivation. These changes need to be recognized early, because during a real mission, they could affect the safety of the entire crew. A space mission cannot succeed through well-functioning machines alone. Equipment can keep the temperature stable, filter water, clean the air, and issue warnings when something goes wrong, but people must still understand those warnings and make the right decisions. They must recognize when another crew member is becoming too tired, know when to continue working, and understand when it is time to stop. The ability to support one another can sometimes be just as important as any device inside the habitat. A year inside the simulated habitat is therefore not a year spent simply waiting for time to pass. It is hundreds of mornings waking beneath the same lighting system, hundreds of checks of the same familiar screens, and hundreds of meals prepared from a carefully calculated supply of food. Each day creates another opportunity for a small mistake to appear, be noticed, and be corrected before it grows into a larger problem. The sealed habitat in Houston can recreate a sense of distance, restrict living space, and force people to use resources more carefully. It can produce monotony, work-related pressure, and situations that require the group to solve problems on their own. But even while the door remains closed, Earth is never truly far from them. Beyond those walls, an entire planet continues performing thousands of tasks that keep their environment stable. Gravity still pulls everything toward the floor, air still surrounds the entire facility, and the temperature outside is still regulated by Earth's oceans, clouds, and atmosphere. In a truly serious emergency, the support team can still open the door and bring the participants outside. These conditions make the simulated habitat far safer than any real base on the Moon or Mars. On the Moon, nearly all of those ordinary protections disappear. There is no atmosphere thick enough for humans to breathe, no natural environment to keep temperature stable, and no rapid rescue route if a critical piece of equipment stops working. Before building a home on another world, human beings must understand just how many functions that home will need to replace functions that Earth quietly performs for us every second. On an ordinary morning, someone stands beside a window and takes a deep breath without checking an oxygen gauge. They pour a glass of water from the faucet, drink it, and step outside without measuring the pressure, temperature, or radiation levels beyond the door. No protective suit needs to be worn, no airtight hatch needs to be sealed, and no control panel has to confirm that the environment is safe. These seemingly simple actions are possible only because an entire planet is quietly working behind them. Inside the simulated habitat in Houston, people can recreate the feeling of isolation, restrict water use, and make the rooms resemble a vehicle traveling through space. Yet beyond the walls, Earth continues to provide the things that matter most. It keeps air surrounding the habitat, creates the gravitational pull that holds everyone to the floor, and maintains an environment the human body has known since birth. Even when no one notices, the planet is functioning like an immense life support system. That system is not contained in a single room, nor is it controlled by one panel of switches. It stretches from the air overhead to the oceans, clouds, soil, forests, and tiny organisms that are almost impossible to see. Each part performs a different role, yet remains closely connected to all the others. Through this combination, water continues to circulate, oxygen is replenished, temperatures are moderated, and many substances essential to life are returned to the cycle. The layer of air surrounding the planet is called the atmosphere. Most of the atmosphere near the ground is nitrogen, followed by oxygen and small amounts of other gases. People do not need to remember every percentage to understand its importance, because a single ordinary breath is enough to reveal that the atmosphere is there. It carries oxygen into the lungs, receives the carbon dioxide released by the body, and creates the conditions in which the blood, lungs, and other organs can function in their familiar way. But the atmosphere does more than provide the gases humans need to breathe. It also creates pressure, the constant force surrounding our bodies. Near sea level, the pressure of the air on every square meter of surface is equivalent to the weight of roughly 10 tons, yet we do not feel crushed beneath it. That is because the pressure inside the body is balanced against the pressure outside, like two silent forces holding one another in a stable state. The human body developed within this balance over an immense span of time. The lungs expand and contract in an environment with suitable pressure, while oxygen can move from the air into the bloodstream because the surrounding conditions remain within a familiar range. If the pressure falls too low, simply supplying oxygen is no longer enough to keep the body functioning normally. This is why a base beyond Earth must do far more than place a few tanks of air inside a sealed room. Beyond Earth's atmosphere lies a region with almost no air, commonly known as a vacuum. The human body cannot be exposed directly to that environment, because the lungs, blood, and tissues all require an appropriate level of pressure to function. A small crack in the wall of a habitat would therefore be far more serious than a draft coming through a window. It could become an escape route for the precious air inside, causing living conditions to change faster than people could respond. On Earth, if a room begins to feel stuffy, we can open a door or window and let fresh air flow inside. Wind, temperature differences, and the natural movement of the atmosphere help keep the air circulating. But inside a base, surrounded by vacuum, there is no fresh supply of air waiting outside. Nearly every molecule that escapes from the habitat is lost, so its walls must preserve the environment within continuously, not merely for a few hours, but for months or even years. The atmosphere also protects Earth from rapid changes in temperature. When sunlight reaches the surface, the land and oceans absorb some of its energy and gradually release it again. Air, clouds, and water vapor help retain, disperse, and transport heat from one place to another. As a result, most of the planet's surface does not instantly become a furnace in daylight and then turn into a frozen landscape as soon as the sun goes down. The oceans also serve as an immense reservoir of heat. Water can absorb a great deal of energy without warming too quickly, while ocean currents and winds carry that heat across long distances. Some of the water evaporates, forms clouds, and eventually returns to the surface as rain or snow. These movements do not make every place on Earth comfortable, but they help protect the planet from many of the sudden changes that a world without oceans or an atmosphere would experience. Even an ordinary rainstorm is part of this life support system. Water evaporates from seas, lakes, rivers, and damp soil, rises into the atmosphere, and condenses into tiny droplets within clouds. After falling back to the ground, it flows across the land, seeps into deeper layers, or returns to rivers and oceans. Along the way, it nourishes plants, carries minerals, and creates environments where countless living organisms can survive. Inside a base beyond Earth, there are no oceans, clouds, or natural rainstorms to perform this work. Water cannot simply disappear down a pipe and be treated as though it has left human life behind. Moisture from breath and perspiration, water used for washing, and many other forms of wastewater must all be collected, purified, and returned to use. Through machinery, the habitat must create a small cycle of its own to replace part of the vast water cycle of an entire planet. Earth is also protected by more than a single layer. High above the surface, the atmosphere absorbs or weakens many forms of radiation that can harm living things. Some of the sun's ultraviolet radiation is reduced by the ozone layer, while the thick atmosphere causes many small rocks from space to heat up and break apart before reaching the ground. The bright streaks we call meteors are often signs that the atmosphere is quietly protecting the surface below. Farther out lies the region of space influenced by Earth's magnetic field. This field can be imagined as an invisible shield surrounding the planet, helping redirect many high-energy particles released by the sunday. It cannot stop everything, nor does it form a perfectly sealed wall, But together with the atmosphere, it makes Earth's surface far safer than worlds with almost no comparable protection. People rarely think about the magnetic field in daily life because it cannot be seen, heard, or touched. Yet whenever the sun releases a powerful stream of particles into space, this invisible shield helps guide their motion around Earth. Near the polar regions, some of those particles interact with the atmosphere and produce auroras. These beautiful bands of light in the sky are also a reminder that the space beyond Earth is not completely still. Once humans leave Earth's protection, radiation becomes a factor that must be considered in every design. A habitat needs shielding materials, safe areas where the crew can take shelter, and instruments that monitor surrounding radiation levels. In some cases, soil and rock from the construction site may be placed over the structure to provide additional protection. The walls must therefore do more than keep air inside. They must also reduce the effects of what is constantly arriving from outside. Earth also sustains life through countless cycles connecting the air, water, soil, and living organisms. Plants use light to grow, absorbing carbon dioxide and releasing oxygen through photosynthesis. Animals and humans consume oxygen, eat plants or other organisms, and return carbon dioxide and waste to the environment. Tiny organisms in the soil continue breaking down material, allowing many substances to re-enter the cycle instead of remaining locked away forever. These cycles are not perfect, nor do they unfold in exactly the same way everywhere, but they reveal that life on Earth has always depended on exchange. What one organism releases may become a source of life for another. Water passes through the body and returns to the environment, while carbon moves between the atmosphere, oceans, rocks, soil, and living beings. The entire planet resembles an enormous network in which matter is constantly transferred from one place to another. Inside a sealed habitat, humans must create a very small version of that network. Every person breathes in oxygen and releases carbon dioxide, while also adding heat, moisture, odors, tiny particles, and many other substances to the air. If the room were completely sealed without any processing system, the simple act of living would gradually change the environment. Hour by hour, the air could become warmer, more humid, and increasingly rich in carbon dioxide. What is remarkable is that oxygen may not be the first problem people notice inside an enclosed space. Carbon dioxide can accumulate to levels that cause headaches, fatigue, difficulty concentrating, and impaired decision-making, even while the air still contains oxygen. A habitat therefore needs systems that continuously remove carbon dioxide from the atmosphere. They must work quietly, steadily, and quickly enough to balance the amount produced by the crew each day. Oxygen must then be replenished in a controlled way. It may be carried in storage tanks, produced from water, or supplied through a combination of different sources. But more oxygen is not always better, because an environment with excessively high oxygen levels can make materials more likely to catch fire. The air system must maintain the proper balance, like carefully mixing the exact proportions of a substance on which everyone inside the habitat depends every minute. Humidity is also part of that balance. Every breath and every drop of perspiration adds more water vapor to the air. If humidity rises too high, moisture can condense on walls, inside equipment, or in hidden areas, creating conditions where microorganisms can grow and metal can corrode. If the air becomes too dry, the skin, eyes, and respiratory system may become irritated, affecting both the crew's sleep and their ability to work. The ventilation system therefore does much more than simply move air around the room. It must carry that air through filters, remove fine particles, control humidity, and help distribute heat more evenly. Sensors continuously monitor oxygen, carbon dioxide, pressure, temperature, and many other substances that people cannot detect with their eyes alone. When one of these values begins to change, the system must recognize it before the crew can clearly feel that something is wrong. The sound of the fans that people hear every day inside the simulated habitat is therefore more than background noise. In a real base, the steady hum of a fan means the air is still moving, the filters are still receiving airflow, and the habitat is continuing to breathe. If that sound suddenly changes or disappears, the silence may become more alarming than any loud noise. The people living inside will learn to listen to the habitat much as sailors listen to their ship, The temperature inside cannot be kept stable simply by building thick walls. Human bodies, computers, lights, cooking equipment, and many other systems constantly generate heat. If that heat is not removed from the living area, the habitat will gradually become warmer, even when the environment outside is extremely cold. Heat must therefore be collected, transported, and released through specially designed systems. Much as the body carries heat toward the skin and cools itself through perspiration and blood flow, waste cannot simply be carried outside the habitat and forgotten. Every bag of trash occupies space. Every amount of wastewater contains materials that may still be recovered, and every portion of leftover food affects the closed environment. A long-term base must sort, process, and reuse as much as possible. The idea of throwing something away becomes difficult to maintain in a place where everything must either be brought from Earth or produced from extremely limited resources. Microorganisms are another part of life that humans cannot leave behind. They exist on the skin, inside the body, on clothing, and on nearly every object brought into the habitat. Many are harmless, or even beneficial. But within a closed environment, some can grow in damp or difficult-to-clean areas. The habitat must therefore control cleanliness, airflow, and frequently touched surfaces without trying to turn the living space into an environment entirely free of life. All of these processes show that a base beyond Earth cannot depend on a single oxygen-producing machine. It needs many smaller systems working together continuously. One to maintain pressure, another to filter the air, another to recover water, another to control heat, and sensors to monitor the entire environment. Each system must respond to the condition of the others, because a small change in one part of the habitat can affect many other areas. If the air circulation system performs poorly, heat and carbon dioxide may begin to accumulate. If the thermal control system develops a problem, electronic equipment may overheat, and the amount of condensation may also change. If water filtration is interrupted, plans for meals, hygiene, and plant care will all be affected. Systems that appear separate are actually connected, much like the organs within a living body. For this reason, the habitat must have several layers of protection rather than placing every life within the care of a single machine. Critical components need backups, spare parts, and manual operating methods for moments when automated systems can no longer be trusted. The crew must also know how to recognize early signs of trouble, because a small warning handled in time can prevent an entire chain of failures. Far from Earth, the ability to repair is just as important as the ability to build. The entire habitat can be imagined as a collection of familiar functions joined together within a single structure. Its sealed outer shell is like skin, keeping the internal environment from escaping. The air circulation system works like lungs, while water filters and waste processing systems perform roles similar to the liver and kidneys. Thermal control allows the habitat to cool itself as the body regulates its temperature, while sensors act like nerves, constantly searching for signs of danger. But this comparison also reveals how fragile a home beyond Earth can be. A living body can heal many small injuries on its own, while a habitat can do so only if humans have prepared the necessary equipment, materials, and repair procedures in advance. A filter cannot replace itself, a crack cannot close on its own, and an inaccurate sensor may provide information that leads the entire crew to make the wrong decision. The habitat remains alive only as long as people continue to care for it. On Earth, most natural systems do not depend on a small group of people waking every morning to check every measurement. Clouds continue to form, rain continues to fall, winds continue to move, and oceans continue to store heat even while humans sleep. Forests, soil, and living organisms continue participating in cycles far larger than any settlement could ever recreate. We are protected by a system that has been operating for billions of years, even though that system still has limits and can be damaged. When humans leave Earth, we do not truly bring the entire planet with us. We can only select its most essential functions and reduce them to the size of a room. Enough air to breathe, a supply of water that can be reused, a system for controlling heat, a shield against radiation, and equipment capable of continuing to operate for thousands of days. Each component is a tiny piece of Earth replaced by metal, pipes, sensors, and software. Living inside such a habitat means seeing the world in an entirely different way. Air is no longer the invisible emptiness between objects, but a resource that must be measured. Water is no longer something that disappears after use, but matter that must be recovered. The sound of a fan is no longer an irritating noise behind a wall, but evidence that the habitat is still keeping the people inside alive. On Earth, we can forget these things because the planet quietly performs them every day. But on another world, only a thin wall will stand between the human body and an environment where life cannot survive. The habitat must become a coat, a pair of lungs, a water treatment plant, and a second skin all at once. It must protect people not only from major dangers, but also from changes so subtle that almost no one notices them at first. And the first place humans hope to carry this miniature Earth is a world that has always been present in the night sky. It is closer than any planet. Close enough that light takes only a little more than a second to travel from there to Earth, and familiar enough that many people can recognize the bright and dark regions across its surface. Yet, behind that peaceful appearance lies an environment with almost no natural ability to protect life. That world is the Moon, where the atmosphere has almost entirely disappeared, temperatures can change dramatically, and every step takes place beneath a black sky with no protective layer of air. To live there, humans will have to bring every small function that Earth normally performs for us. And only when we place that miniature Earth on the lunar surface will we begin to understand just how unforgiving our nearest neighboring world truly is. Earth hangs above the lunar horizon, blue and luminous against a completely black sky. From that cold gray surface, our home planet appears so close that a person might imagine reaching out and touching it. Yet between the two worlds lies a vacuum, stretching roughly 384,400 kilometers. Enough space to line up nearly 30 Earths from end to end. Light crosses that distance in just over a second, while a crewed spacecraft needs several days. Compared with Mars, the Moon is right next door. The Apollo missions of the past took only about 3 days to carry humans from Earth to the vicinity of the Moon, while a journey to Mars may last 6 to 9 months. The shorter distance makes it easier to transport supplies, communicate, and receive support from Earth. For this reason, the Moon is often seen as the ideal place for humanity to learn how to build a permanent base before traveling farther. But close does not mean gentle. When we look at the Moon from Earth, we see a familiar object that has appeared in the sky for thousands of generations. Its soft light is associated with quiet nights, ocean tides, and the rhythms of many cultures. Yet that glow is only sunlight reflected from a dry, cold surface with almost no natural ability to protect life. On Earth, before stepping outside, people only need to wear clothing suited to the weather. On the Moon, passing through the habitat door means leaving behind the entire artificial environment keeping the body alive. A suit worn outside is not simply protective clothing. It must become a small room that can be carried along. It has to provide air, maintain pressure, regulate temperature, remove the gases a person exhales, and shield the body from the surrounding environment. The Moon has an extremely thin layer of gases known as an exosphere, but it is entirely different from Earth's atmosphere. The atoms and molecules there are so widely separated that they rarely collide before drifting away or falling back toward the surface. There is no wind in the way we experience it on Earth, no clouds moving across the sky, and no layer of air thick enough to carry sound. A person standing outside the habitat would not be able to hear the footsteps of someone walking right beside them. Even though the exosphere contains tiny amounts of atoms such as helium, neon, hydrogen, and argon, humans still cannot breathe from it. There is far too little gas to create the pressure required for the lungs and body to function. A lunar habitat must therefore hold all of its air inside through its walls, joints, and sealed doors. Even a small opening could allow that air to begin escaping into the space outside. On Earth, a small hole in a wall usually causes little more than a draft or allows rainwater to seep inside. On the Moon, the difference between the pressurized air within and the vacuum outside makes every crack far more serious. Air will search for a way out, and the habitat must detect the change early enough for the crew to respond. An unfamiliar sound, a number slowly falling on a display, or a faint stream of moving air may be signs of a problem that requires immediate attention. The habitat can be imagined as a sealed container, placed in an almost empty expanse. Inside are stable temperatures, breathable air, and people going about their daily lives. Outside is an environment that cannot support the human body for even a short time. The wall between them must therefore be strong enough to withstand the pressure difference while remaining airtight enough to preserve every precious part of the atmosphere within. Vacuum also changes the way heat moves compared with ordinary life on Earth. Here, air can carry heat from warmer places to colder ones, while wind helps cool the skin and equipment. On the Moon, there is almost no air to perform this work. Heat is gained mainly from sunlight or lost through thermal radiation, which means surfaces exposed to the sun and surfaces hidden in shadow can experience very different conditions. When sunlight shines directly on regions near the lunar equator, surface temperatures may rise to around 127 degrees Celsius. That is hotter than the boiling point of water under ordinary conditions on Earth. In darkness, temperatures may fall to about minus 173 degrees Celsius, cold enough to make many materials brittle and freeze many kinds of liquids. During a single cycle of day and night, the same habitat may have to endure both intense heat and extreme cold. Day and night on the Moon do not change as quickly as they do on Earth. The Moon takes about 29.5 Earth days to complete one full cycle of illumination as seen relative to the Sunday. In many regions, this means the surface may remain in continuous sunlight for nearly 2 weeks, followed by almost 2 weeks of darkness. Heat does not simply rise or fall over a few hours. It can accumulate or escape for days at a time. Imagine a house with one wall facing a furnace that burns continuously for nearly half a month, while the opposite side faces a deep freezer. Then the entire situation reverses when the sun sets and darkness lasts for many days. The habitat walls must withstand those changes without bending, cracking, or damaging their airtight layers. Pipes, electrical cables, solar panels, and equipment placed outside must also continue working as materials repeatedly expand in the heat and contract in the cold. Inside the habitat, the temperature cannot be allowed to follow the conditions on the surface outside. The system must collect heat from human bodies, machinery, and artificial lighting, then carry that excess energy away from the living area. When the external environment becomes extremely cold, the habitat must also prevent heat from escaping too quickly. Temperature control therefore becomes a continuous process, not simply a matter of switching on a heater or cooling unit and allowing it to run on its own. The long cycle of day and night also affects the power supply. Solar panels can produce energy while the surface is illuminated, but in regions that experience many days of darkness, the habitat needs a way to store enough electricity or must rely on additional sources of power. Electricity is used not only for lights and computers, but also to maintain air, water, temperature, communication, and many other critical systems. When the power stops, the habitat begins to lose its ability to keep the internal environment stable. This is one reason the regions near the Moon's south pole have received so much attention. Because the Moon's rotational axis is tilted by only a small angle, some elevated locations near the pole may receive sunlight for much longer periods than many other regions. At the same time, some deep craters nearby are almost never touched by sunlight. The combination of extended illumination and permanently cold shadowed areas makes this region important for plans involving long-term exploration. Even so, no carefully chosen location can turn the Moon into an easy place to live. The Moon has almost no atmosphere to soften the heat, retain warmth during the night, or redistribute energy from the Sunday. There are no clouds to reduce the incoming light and no wind to carry heat elsewhere. Every area exposed to sunlight or hidden in shadow must face its conditions directly. Beyond temperature and vacuum, radiation presents a challenge that is more difficult to see. On Earth, the atmosphere and magnetic field help reduce the effects of many high-energy particles arriving from the sun and deep space. The Moon today has no global magnetic field like Earth's, and its exosphere is far too thin to provide meaningful protection. Its surface is therefore more directly exposed to the radiation environment of space. Most forms of radiation cannot be immediately felt by the skin, eyes, or ears. A person cannot see the high-energy particles moving through the surrounding environment, yet the body may still absorb some of their energy. Over long periods of exposure, radiation can affect cells and increase health risks. A brief visit and a life lasting many years are therefore two entirely different challenges. Solar activity is not always steady. At times, the sun releases powerful streams of particles into space, creating bursts of radiation above normal levels. On Earth, most people continue with their daily lives without even realizing that such an event is taking place. On the Moon, however, the crew may need to stop working outside and move into a more heavily shielded area of the habitat. A radiation shelter may require thick layers of material or be placed deeper beneath the surface. Water, construction materials, and layers of lunar soil and rock can all help reduce the amount of radiation that reaches the interior. This means a future base may not resemble a house with many windows looking out across the landscape. Sometimes, the safest place may be a room hidden behind several protective layers, where the outside sky can be seen only through cameras and screens. The Moon also lacks a thick atmosphere capable of burning up most of the small pieces of rock arriving from space. On Earth, many small objects heat up and disintegrate as they pass through the air, creating the streaks of light we call meteors. On the Moon, tiny fragments of matter can strike the surface directly at high speed. Most are extremely small, but over time, these impacts can still wear down or damage equipment placed outside. A habitat therefore needs more than airtight walls. It also requires several layers of protection and the ability to be repaired. Critical components should not remain fully exposed when shielding is possible, while pipes and cables must be arranged so that one small failure does not disable the entire system. The crew needs sensors capable of detecting leaks, materials for sealing damage, and ways to isolate individual sections when something goes wrong. On the Moon, the ability to continue operating after damage occurs is just as important as the ability to prevent that damage in the first place. The Moon's gravity is only about 1/6 as strong as Earth's. A person with a mass of 60 kilograms still contains the same amount of matter, but their weight on the surface would feel equivalent to only about 10 kilograms on Earth. This makes objects easier to lift, allows steps to become longer, and gives the body more time before returning to the ground. Footage from the Apollo missions shows astronauts moving with their distinctive bouncing steps for precisely this reason. But weaker gravity does not mean that every task becomes effortless. An object may be easier to lift, yet it still has inertia and can remain difficult to stop once it begins moving. A bulky protective suit restricts movement in the arms and legs and narrows the field of vision, making it harder to bend down, turn around, or use tools. One misplaced step can cause a person to lose balance, while standing up inside a sealed suit is far more complicated than rising after a fall on Earth. Living for long periods in low gravity also raises questions about the human body. On Earth, bones and muscles are maintained in part because they must constantly work against gravity. In the near weightless environment of space stations, the body can lose muscle and bone if exercise is not performed regularly. The Moon still has gravity, but only 1/6 of Earth's, and humans have never lived under that level of gravity long enough to fully understand its effects over many years. For this reason, a lunar base needs more than sleeping quarters, work areas, and storage rooms. It also requires exercise facilities that place regular physical stress on the body, along with long-term health monitoring programs. Researchers must determine how much movement people need, what they should eat, and how they should rest in order to preserve their ability to work. Being able to walk on the Moon for a few days does not automatically mean that the body will adapt well after months or years. Low gravity also changes the way liquids, dust, and objects move. A spilled drop of water will still fall toward the floor, but more slowly than it would on Earth. A tool that is thrown may travel farther than expected, while disturbed material may take longer to settle. Every familiar task, from transporting equipment to constructing buildings, must be tested again under conditions in which the human body has very little experience. Even the amount of time spent working outside cannot be determined solely by an astronaut's endurance. The suit must maintain temperature, provide oxygen, and remove carbon dioxide throughout the excursion. Battery power, cooling water, and communication systems all have limits. Every minute outside the habitat must therefore fit within a carefully calculated plan, and the route back must always be considered before anyone travels farther away. If someone experiences an emergency on Earth, An ambulance may arrive within minutes, or a helicopter may carry them to a hospital. On the Moon, even though Earth is only a few days away by spacecraft, help cannot arrive immediately. The crew must be capable of providing initial medical treatment, repairing a suit, assisting an injured person, and returning them safely to the habitat. The familiar sight of Earth in the sky does not shorten the distance to rescue. Communication between Earth and the Moon is far faster than communication with Mars, but it is still not completely instantaneous. A radio signal takes more than a second to travel one way, meaning that a question and its reply may create a pause of several seconds. This delay is not especially disruptive during ordinary conversation, but it is enough to make remote control of machinery feel slower. The crew must still handle situations that demand an immediate response on their own. The Moon also has a feature that makes its sky look entirely different from Earth's. Because there is no thick atmosphere to scatter light, the sky remains black even when the sun is shining brightly. Shadows on the surface can be extremely deep, and the boundary between light and darkness becomes sharply defined. A rock hidden in shadow may be difficult to see, while the illuminated ground beside it may appear painfully bright to both eyes and cameras. This directly affects the way people move and work. Astronauts need artificial lighting, cameras, and sensors to observe areas where the eyes cannot adjust quickly enough. Rovers must detect deep holes, protruding rocks, and changes in the terrain under conditions of intense contrast. A path that appears smooth from a distance may contain dark regions, concealing obstacles directly in front of the wheels. The view may be beautiful, but beauty on the Moon is always accompanied by fragility. Through the window of the habitat, Earth may appear as a small blue sphere suspended in darkness, containing every ocean, forest, city, and loved one known to the crew. Simply looking at it may make home feel close, yet not a single breath of air, drop of rain, or gust of wind from that planet can cross the vacuum to reach them. Everything required for life must remain inside the habitat or travel with the crew inside their protective suits. Pressure must be maintained, temperature controlled, radiation monitored, and backup sources of power kept ready. A single door may separate a warm room from a surface heated like a furnace, or divide breathable air from darkness approaching -173°C. Every layer of material within that door carries responsibilities that, on Earth, are normally shared by an entire planet. Even so, the Moon remains a logical place for humanity to begin learning how to live beyond Earth. It is close enough to reach within a few days, distant enough for the conditions of space to become unmistakable, and harsh enough to expose weaknesses in our technology. What we learn there may help us design stronger habitats, more durable suits, more reliable power systems, and more realistic rescue plans before moving on to Mars. But building a sustainable lunar base is not only about resisting major threats such as vacuum, radiation, or extreme temperatures. Some dangers do not arrive with an explosion, do not immediately turn a display red, and cannot be clearly seen from a distance. They accumulate little by little, cling to equipment, and follow people through the doorway after every excursion. Most of the Moon's surface is covered by a layer of material formed through billions of years of impacts. It may look like sand or fine gray powder, but it has not been worn smooth by wind and water as rocks and soil are on Earth. These tiny particles can cling to boots, gloves, joints, and every surface carried outside. They are small enough to be nearly invisible, yet persistent enough to work their way into every opening in the habitat. Heat, cold, vacuum, and radiation are all conditions humans know they must prepare for before stepping onto the Moon. But the dust lying quietly beneath their feet may return with them after every excursion, slowly scratching materials and coating the most important equipment. In a place where every door must preserve airtight conditions, even a single tiny grain of dust can become a problem that cannot be ignored. An astronaut returns to the habitat after spending several hours working on the lunar surface. The suit, once bright white, is now covered in a thin layer of gray, especially around the boots, knees, and joints that move most often. When the outer door closes, the astronaut steps into the airlock, the sealed chamber between the airless world outside and the safety of the living quarters. But the dust beyond the habitat does not stop at the door. It remains clinging to the gloves, the edges around the helmet, and the folds of the suit. Some of it rests on tools, cameras, and storage containers brought back from the excursion. Beneath the lights of the airlock, the tiny particles appear to be nothing more than an unremarkable layer of gray powder. Yet, in a place where every seal must remain airtight and every piece of equipment must operate reliably, this dust is far more than a stain that needs to be wiped away. Most of the moon's surface is covered by a layer of material known as regolith, made up of fine dust, broken rock, and mineral fragments of many different sizes. This layer did not form over a short period of time. It developed across billions of years as meteorites and smaller pieces of rock repeatedly struck the surface. Each impact crushed existing rock into smaller fragments, threw them upward, and allowed them to fall back under the moon's weak gravity. On Earth, rocks also break apart and become sand or soil, but the particles continue to change under the influence of water, wind, and weather. They are carried through rivers, collide with one another on beaches, or roll across the ground for long periods of time, gradually rounding many of their sharp edges. On the moon, there are no flowing rivers, no rain, and almost no wind to perform this work. As a result, many dust particles retain sharp edges and rough surfaces. From a distance, regolith may resemble a quiet layer of gray sand. Seen more closely, however, it is the result of countless impacts that have occurred since the moon was young. Some particles are simply fragments of pulverized rock, while others were once melted by the heat of an impact and fused with nearby material. They may have irregular shapes, with tiny corners sharp enough to scratch surfaces and cause wear when they become trapped inside moving components. Every step an astronaut takes disturbs the regolith. Because lunar gravity is only about 1/6 as strong as Earth's, particles kicked upward can rise higher and take longer to return to the surface. Rover wheels can also throw dust into long trails behind them, coating nearby equipment. There is no wind to carry the dust elsewhere, but there is also no rain to wash clean the surfaces that have turned gray. This dust can cling far more strongly than many people might imagine. Ultraviolet light from the sun and particles carried by the solar wind can electrically charge the surface of the regolith. The smallest grains may then be attracted to suits, visors, solar panels, and other materials, much like a small piece of paper clinging to an object after it has been rubbed. Simply shaking the dust off or brushing it away by hand may not always be enough to make it fall. Apollo astronauts discovered that lunar dust followed them back into their spacecraft after surface excursions. Even though they tried to brush the dust from their suits before entering, a considerable amount remained attached to the fabric, boots, and equipment. Inside the small cabin, particles could break free, drift through the air, and settle onto other surfaces. Their experience showed that dust was not merely an outdoor problem. It could quickly become part of the living environment inside. During a short mission, a thin coating of dust may be little more than an inconvenience. But a habitat operating for months or years must endure thousands of departures and returns. Each one carries another small amount of regolith into the doorway, the airlock, and the equipment storage areas. The dust from any single excursion may seem insignificant, but its slow accumulation is what concerns engineers. It can be compared to a house beside a beach, where sand appears indoors even when the doors are closed carefully. It collects inside shoes, on clothing, beneath rugs, and in corners that are difficult to clean. Yet sand on Earth usually does little more than make a home dirty or feel unpleasant beneath bare feet. Lunar dust can go much farther, because it settles on equipment upon which the survival of the entire crew depends. The joints of a protective suit are among the most vulnerable areas. The arms, knees, wrists, and many other sections must move thousands of times during a single excursion. If dust enters between layers of material rubbing against each other, it can act like a very fine abrasive powder. Over time, repeated movement can scratch surfaces, wear away protective layers, and make the joints increasingly stiff. A lunar suit does more than protect its wearer from heat or cold. It must maintain pressure, supply oxygen, remove carbon dioxide, and create a stable environment around the body. Wear in a seemingly minor area can, therefore, never be ignored. If a seam gradually loses its airtight seal or a joint no longer moves correctly, the astronaut may encounter serious difficulty while far from the habitat with no quick way to make repairs. The helmet visor must also be protected. Dust settling on its surface can reduce visibility, especially when intense sunlight creates severe glare. If the astronaut tries to wipe the dust away with a glove, the sharp particles may leave tiny scratches on the visor. A single scratch will not cause the material to fail immediately, but after repeated cleaning, the view may become less clear and make it harder to observe the terrain. The same problem affects cameras and scientific instruments. A thin layer of dust on a lens can blur an image or alter the amount of light reaching a sensor. Precision instruments sometimes rely on surfaces that must remain clean in order to function correctly. If dust covers them, the data they produce may no longer be reliable, even when the equipment shows no obvious sign of damage. Solar panels are also particularly vulnerable. To generate electricity, their surfaces must receive direct sunlight. As dust accumulates, part of that light is blocked, and the amount of power produced may gradually decline. A very thin layer may not cause a major change at first, but if the habitat depends heavily on solar energy, even a small and lasting reduction can force the crew to adjust the way electricity is used. On Earth, rain can wash some dust from rooftops and solar panels. Wind can also carry away loosely attached particles, though it may sometimes bring more dust with it. On the Moon, these natural cleaning processes are almost entirely absent. Once a surface becomes covered, it remains that way until humans, robots, or a specially designed system clean it. Dust may also affect the ability of equipment to release heat. Many machines outside the habitat must radiate the heat they produce while operating. If a heat-dissipating surface becomes coated with an unwanted layer of material, its ability to exchange heat may change. The equipment may then grow hotter than expected, while sensors and electronic systems generally operate properly only within a limited temperature range. Mechanical components such as hinges, gears, and bearings must also be protected carefully. On Earth, lubricants and protective coverings help moving surfaces operate smoothly, but vacuum and extreme temperatures make the choice of materials more complicated. When regolith enters between components, it can increase friction and make movement progressively more difficult. A robotic arm or rover wheel may slowly lose efficiency without failing all at once. The seals around habitat doors are among the most critical areas. Every time a door opens, dust can settle along the edges, grooves, and contact surfaces of the gasket. When the door closes, particles trapped between the two surfaces may prevent them from fitting together completely or create tiny scratches. If this process is repeated thousands of times, the ability to contain air may gradually weaken even though no large crack has appeared. This is why an airlock is used not only to balance pressure between the interior and exterior. It must also serve as a barrier against dust before people move deeper into the living area. Suits, tools, and storage containers need to be inspected, cleaned, or kept in a separate section. The air inside the chamber may need to pass through special filters that collect fine particles released from their surfaces. Some habitat designs attempt to keep most of the suit outside altogether. Instead of putting on the suit indoors and then walking through a doorway, an astronaut could enter it through a port in the back, while the suit's exterior remains exposed to the lunar environment. This arrangement may reduce the amount of regolith carried into the living quarters, because the dusty boots, knees, and outer surfaces never have to pass through the clean interior. However, no single method can remove lunar dust completely. Excursions outside the habitat still require tools, rock samples, cameras, and many other items that must be brought back inside. Robots can also carry dust on their wheels, arms, and moving parts. Dust control must therefore be treated as a multi-layered process, with each layer stopping some of the particles before they can travel deeper into the habitat. The first layer may begin with the design of the surfaces themselves. Certain materials and coatings can make dust less likely to cling or easier to remove. Joints can be shielded to reduce the chance of regolith working its way inside, while critical edges and seals can be arranged so that dust is less likely to collect. Equipment can also be designed with fewer gaps and crevices, making cleaning simpler and faster. The next layer includes mechanical methods of removing dust, such as brushes, controlled air jets inside enclosed areas, or devices that create gentle vibrations. But brushing is not always safe. because sharp particles can scratch the surface being protected. Air jets must also be used in a controlled space, or the dust may simply move from one piece of equipment into the entire room. Every cleaning method must therefore consider where the particles will go after they leave the surface. NASA and other research teams are also developing technologies that use electrical forces to move dust. These systems are often called electrodynamic dust shields. They work by creating changing electric fields across a surface, causing electrically charged regolith particles to be pushed or carried away from the protected area. Instead of being scrubbed with a brush, the surface may be able to clean itself through an invisible force. This idea is especially useful for areas that are difficult to reach, including solar panels, optical surfaces, radiators, and scientific instruments. If the system can operate reliably, it may reduce the number of times astronauts need to go outside simply to remove dust. Every spacewalk consumes time, energy, and suit resources, so an automatic technology that keeps surfaces clean may offer benefits far greater than its simple appearance suggests. During the Blue Ghost 1 mission in 2025, an electrodynamic dust shield was tested directly on the Moon. The experiment allowed researchers to observe how the technology performed in low gravity, vacuum, and real lunar regolith, rather than relying only on simulated material in laboratories on Earth. It is not the only possible solution to the dust problem, but it represents an important step toward understanding whether future surfaces can actively push lunar dust away. Testing on the Moon is necessary because laboratory simulants cannot fully reproduce the billion-year history of real regolith. The shape, size, electrical charge, and adhesion of the particles can vary from one location to another. A technology that works well inside a clean room on Earth may not perform in exactly the same way under direct sunlight, in vacuum, and through extreme changes in temperature. Researchers are also concerned about how dust may affect human health. If fine particles enter the living quarters and remain suspended in the air, they can be inhaled or come into contact with the eyes and skin. Regolith is not identical to ordinary household dust, because it contains sharp particles that have been exposed to the radiation environment of space for long periods of time. A habitat therefore needs filtration systems capable of keeping airborne dust at safe levels. Dust on the skin or inside the eyes may cause irritation, especially when there is not enough water available for washing as there is on Earth. Cleaning suits and the human body must also be planned carefully so that it does not consume too many resources. A crew member cannot simply stand beneath a powerful shower after every excursion, because all of that water must be collected, purified, and returned to the system. Dust control is therefore directly connected to the management of both water and air. Air filters can capture many small particles, but the filters themselves must be monitored and maintained. As dust accumulates, airflow may decrease, forcing the fans to work harder to keep the air circulating. If a filter becomes clogged, air quality inside the habitat may change while the system consumes more electricity. The crew must know when to clean, replace, or safely handle the dust collected by the filters. Even the dust that has already been gathered cannot simply be dumped into a corner. If it is not sealed away, it may cling to tools and return to the living area. In a long-term habitat, procedures must be clear from the moment dust is detected and collected to the point when it is returned outside or used for another purpose. Every material must have a destination, because the interior is far too small for unwanted substances to accumulate without limit. Regolith is not only an enemy. The same material covering the lunar surface may become an important resource for future bases. It could be used to cover habitats, adding protection against radiation, and reducing the effects of small fragments arriving from space. Some plans also explore using regolith as a construction material for roads, landing pads, or shielding blocks, reducing the amount of material that must be transported from Earth. But using regolith does not mean it can be carried freely into the places where people live. Just as soil on Earth can be used for farming and construction, but should not cover the floor of a bedroom, lunar dust must be controlled according to location. Outside, it may serve as a building material and protective layer. Inside, it must be treated as an abrasive contaminant and kept at the lowest possible level. A landing site provides a clear example of how dust can affect an entire base, When a spacecraft descends, exhaust from its engines can blast regolith outward at high speed. The particles no longer drift gently like dust disturbed by a footstep, but may strike nearby equipment, solar panels, and structures. Landing zones must therefore be placed far enough away or reinforced to reduce the amount of material thrown into the surrounding area. Rover routes may also be prepared to limit dust. If wheels repeatedly cross loose regolith, they can create clouds of particles and carry more material back toward the habitat. A compacted or specially treated surface may reduce the amount of dust disturbed. Structures as simple as roads and parking areas therefore become part of the life support system. Time makes the problem even more complicated. A new habitat may remain clean during its first few weeks, when every filter, seal, and surface is still in its best condition. After a year, small scratches may begin to appear, while dust collects in places that are difficult to reach. After many years, the crew must deal with aging equipment, materials that have endured hundreds of heating and cooling cycles, and components that no longer seal as tightly as they once did. Long-term settlement requires more than technology that works well when it first arrives on the moon. Equipment must be inspected, cleaned, repaired, and replaced on site. A dust-resistant coating can wear away. A filter can reach the end of its useful life, and even a brush can break. If every replacement must wait for a shipment from Earth, the base is not yet truly capable of sustaining itself. The crew must therefore be trained to treat dust as part of every task performed outside. Before leaving the habitat, they need to inspect protective coatings on equipment and identify areas that should be avoided. When they return, they must follow a careful cleaning sequence so that dust does not move from their boots to their gloves and then spread across other surfaces. A few additional minutes in the airlock may prevent many hours of repairs later. Monitoring systems may also track dust using cameras, light sensors, or instruments that measure air quality. A layer too thin to notice easily may still reduce the performance of a solar panel. Data collected over time allows the crew to know when cleaning is needed instead of waiting until a device shows an obvious decline. Inside a sealed habitat, early detection is always safer than dealing with the consequences. The most troubling thing about lunar dust is not any single particle. One grain clinging to a boot will not immediately cause the habitat to lose pressure, and one tiny scratch will not make a machine stop working at once. The danger appears when these small effects are repeated across thousands of footsteps, thousands of door openings and closings, and thousands of movements within mechanical joints. Damage develops so slowly that people may grow accustomed to it before they recognize the problem. Dust, therefore, becomes a test of patience. It requires people to clean surfaces even when they do not yet appear especially dirty, replace filters before airflow declines severely, and inspect seals even when no leak warning has appeared. These repetitive tasks may lack the heroic appearance of setting foot on another world, but they determine whether the habitat will remain safe after many years. Beyond the window, the lunar surface remains as silent as it has been for billions of years. No storm is blowing dust toward the habitat, and there is no sound of sand striking the walls. Yet every excursion carries a tiny part of that world closer to the human living environment. The boundary between outside and inside must therefore be protected through countless actions that may seem insignificant. When the airlock door closes, the dust clinging to a suit does not disappear. It waits to be found along seams, inside joints, and in hidden corners around the boots. Some may be removed with brushes, some captured by filters, and some may remain until the next inspection. The struggle against regolith does not end after one excursion. It begins again every time the outer door opens. But keeping dust outside is only one of the habitat's quiet, continuous battles. While filters work to prevent gray particles from spreading through the air, another system must constantly recover something transparent and far more precious. It appears in every breath, every meal, every drop of perspiration, and every act of personal hygiene performed by the crew. On Earth, water can flow down a sink and disappear from sight. On the moon, the habitat cannot allow a single drop to leave the cycle without trying to recover it. Keeping dust outside is a never-ending struggle. But within the sealed walls lies another task, just as important: ensuring that every drop of water continues to find its way back to life. A drop of water falls into the sink and disappears down the drain. On Earth, this moment is so ordinary that almost no one stops to wonder where the water will go. It joins the wastewater, flows away from the house, and vanishes from sight within seconds. But inside a base on the moon, that drop cannot be allowed to disappear so easily. As soon as water leaves a cup, the human body, or a sink, it must still be recovered. It may become moisture in the air, remain trapped in a towel, mix with wastewater, or settle as a thin film on a cold surface. Whatever form it takes, it remains part of the limited resource on which the entire base depends. In a sealed environment, pipes do not carry water far away. They send it on a journey through purification so that it can eventually return. Water lies at the center of nearly every plan for long-term life beyond Earth, not simply because people need to drink it each day. It is used to prepare food, clean the body, wash tools, care for crops, and support many technical systems. Some water also helps regulate temperature, produce oxygen, or carry heat through equipment. If the water supply develops a problem, the effects will spread into almost every other activity within the base. People can survive for many days with very little food, but a lack of water quickly becomes dangerous. The body needs water to maintain blood volume, regulate temperature, support digestion, and deliver nutrients to cells. Every breath, every drop of perspiration, and every trip to the bathroom removes some water from the body. On Earth, we simply drink more, but beyond Earth, every source of replacement is limited. A small crew living for only a few days could bring all the water it needs from Earth. But when a mission lasts for months or years, that mass increases very quickly. Each liter of water has a mass of nearly 1 kilogram, not including its container, plumbing, or protective equipment. Carrying large quantities of water away from Earth means a rocket must lift more mass, use more fuel, and leave less room for food, equipment, or construction materials. If a base must wait for water to be delivered from Earth, every life inside remains dependent on launch schedules and transportation. A delayed shipment, a rocket failure, or damage to a storage tank could disrupt the entire plan. On the Moon, supplies may arrive within a few days after launch, but preparing a flight cannot happen instantly. A long-term base therefore cannot treat water as something that can simply be reordered when supplies begin to run low. The clearest solution is to reuse as much water as possible. A glass of water consumed in the morning does not end its journey after passing through the body. Some becomes water vapor in the breath, some escapes through the skin, and some enters the wastewater system. The base must recover these sources, carry them through several stages of treatment, and turn them into usable water once again. Human breath always contains moisture. Inside a sealed room, that moisture accumulates alongside water released through perspiration, cooking, and personal hygiene. The humidity control system condenses some of this vapor, much like the droplets that appear on the outside of a cold glass. Instead of allowing the water to run onto the floor or become a hidden problem inside the walls, the base collects it and sends it into the treatment system. Household wastewater is not treated as something entirely useless either. It may contain soap, dirt, salts, microorganisms, and many other substances that make it unsafe to drink directly, but most of what it contains is still water. Filters, treatment membranes, and other purification methods gradually remove those impurities. After several stages of testing, the water can return to the shared supply and be used for a new purpose. The process is not as simple as passing water through a screen and drinking it again. Larger particles may be removed first, but dissolved substances, microorganisms, and extremely small molecules require different methods. The water may need to pass through absorbent materials, specialized membranes, evaporation and condensation systems, or disinfection equipment. Each stage addresses a different problem before the water can be considered safe. Sensors must monitor water quality continuously because clear water may still contain substances invisible to the human eye. Taste, smell, clarity, and temperature reveal only a small part of the answer. The system must detect unwanted compounds before they accumulate to dangerous levels. In a base far from Earth, Knowing that the water is clean is just as important as having the ability to clean it. An effective recycling system can recover most of the water that has been used, but almost no artificial cycle is completely closed. Some water may remain trapped in solid waste, filter materials, food, or replaced components. A portion may be lost through small leaks, outside excursions, or maintenance procedures. Even a base with highly efficient water recycling must therefore monitor its losses and maintain a source of replacement. This gives every drop of water a value far greater than its appearance suggests. A slowly leaking valve does not merely create a small puddle on the floor. Over several weeks, it can gradually reduce the reserve supply. A poorly functioning filter does not simply affect the taste. It may force the entire system to stop for inspection. The crew must learn to recognize subtle signs such as changes in pressure, humidity, or flow rate before they develop into major failures. Water inside the base can be imagined as a small group of people constantly exchanging roles. In the morning, it rests inside one crew member's drinking glass. By noon, some of it has become moisture in the air, while another portion has entered the wastewater system. It then travels through filters, storage tanks, and pipes before appearing days later in a meal, another bottle, or a tray of growing plants. Its return should not be seen as something unpleasant. On Earth, water has already passed through cycles far longer than any human lifetime before reaching us. A raindrop may once have rested in the ocean, risen into a cloud, fallen onto a mountain, traveled through a river, and seeped into the ground. The water in a glass today may have passed through countless organisms and landscapes before being filtered and made safe. The difference lies in the scale of the cycle. Earth uses oceans, the atmosphere, rocks, soil, sunlight, and countless living organisms to move water through an immense system. A lunar base must perform part of that work inside a few rooms, using pumps, pipes, and filters of limited size. Nature may take years to complete a water journey, while the habitat must accomplish it within hours or days. The artificial cycle also requires energy. Water does not move through filters on its own, separate itself from waste, or disinfect itself. Pumps must push it through pipes. Equipment must generate heat or pressure, and sensors need electricity to monitor quality. When people speak about a base's water supply, they are therefore also speaking about its power supply, spare parts, and ability to make repairs. If the power supply is interrupted briefly, water may remain safely inside the storage tanks, but the purification process may slow down. If a pump fails, the water cannot reach where it is needed, even when the total reserve is still sufficient. A base may possess thousands of liters of water and still face danger if it cannot move or process them. A resource becomes truly useful only when the systems surrounding it continue to function. Water must also be stored carefully to prevent microorganisms from growing inside pipes and tanks. A sealed, moist environment with a stable temperature can allow biofilms to form on surfaces. These layers may clog pipes, interfere with sensors, or alter water quality. The system must therefore be cleaned, disinfected, and inspected on a schedule even when the water still appears completely normal. Long stretches of pipe and areas with little flow require particular attention. If water remains still for too long, its temperature and composition may begin to change. Engineers must design the network so that water circulates evenly and does not create too many places that are difficult to reach. The crew also needs ways to collect and test samples without dismantling the entire system. Water used for different purposes does not always need to meet the same standard of purity. Drinking water and water used for food preparation require the highest quality, while water intended for certain technical tasks may be treated differently. Dividing the supply carefully can reduce the energy and time required for purification, as long as the pathways are controlled to prevent mistakes. An efficient base must know how pure each drop needs to be before sending it to its destination. Personal hygiene must also change. On Earth, someone can leave a shower running for several minutes without knowing exactly how much water has been used. Inside the base, every wash uses a smaller amount and follows a method that makes recovery easier. Damp towels, low-flow sprays, and specialized cleaning materials may replace the experience of standing beneath a strong stream of water. This does not mean that people must live in unclean conditions. Hygiene remains essential to the crew's health, comfort, and emotional well-being. But cleaning the body, clothing, and living environment must be adapted to a place without an endless supply of flowing water. Every activity must balance human needs against the processing capacity of the system. Washing clothes is one example of a task that seems simple but is surprisingly difficult to solve. An ordinary washing machine uses a great deal of water and electricity while producing wastewater filled with detergent and fabric fibers. On short missions, clothing can be worn for longer periods and then stored rather than washed. But in a settlement expected to last for years, people will need more durable materials, more efficient cleaning methods, and ways to capture tiny fibers before they clog the filters. Cooking also sends water into many different parts of the cycle. It may be used to soften dried food, prepare drinks, or create steam during meal preparation. Some of it enters the body, some escapes into the air, and some remains in leftover food. The system must account for every one of these pathways because water does not disappear. It merely changes from a form that is easy to see into one that is more difficult to recover. Plants inside the habitat also need water, but they do not simply retain everything delivered to their roots. Some becomes part of their growth, while much of it eventually escapes through the leaves as moisture. Inside a sealed environment, that water vapor can be collected from the air and returned to the system. The growing area therefore consumes water while also becoming part of the habitat's water cycle. However, soil or other growing materials can retain a considerable amount of water. If too much is supplied, it may collect around the roots, damage the plants, and become difficult to recover. If too little is provided, the plants weaken and the supply of fresh food is affected. Moisture sensors and precise irrigation systems help deliver water to the right place at the right time, rather than relying on intuition as someone might in an ordinary garden. Even if the habitat recovers most of its water, carrying the entire initial supply from Earth would still create an enormous burden. For this reason, humans are searching for ways to obtain water directly from the moon. There, water does not exist in rivers, lakes, or easily accessible underground reserves. Most of the hope is focused on regions near the lunar poles, especially craters that have received no sunlight for extremely long periods. These areas are known as permanently shadowed regions. Because of their position near the poles and the shape of the terrain, sunlight cannot reach the floors of certain deep craters. Temperatures there can remain extraordinarily low for long periods, allowing these places to act like natural cold traps. Water molecules that reach them may freeze and remain there instead of quickly escaping into space. Several missions have found evidence that water ice exists within permanently shadowed regions near the lunar poles. The water may be mixed with regolith, trapped in tiny grains, or distributed unevenly beneath the surface. It does not necessarily form clear blocks of ice that people can simply dig up and melt. Determining exactly how much water is present, where it lies, and how it is distributed remains an important part of lunar exploration. Finding evidence of water and being able to use that water are two very different steps. Machinery must operate within an extremely cold and dark environment, excavate or collect material, and then carry it to a processing area. The regolith must be heated to release water vapor, which is then captured and condensed. The entire process requires electricity, equipment capable of surviving extreme cold, and ways to prevent dust from damaging moving components. Permanently shadowed regions are also extremely difficult places to work. There is no natural sunlight for solar panels to generate power on site. The terrain may be steep, and crater walls can sometimes block communication. Machinery must rely on power transmitted from elsewhere, stored batteries, or independent energy systems. Simply lowering equipment into a deeply frozen region and keeping it operational is already a major challenge before any water can be extracted. If ice is mixed with regolith at a low concentration, a large amount of material may need to be processed to obtain a relatively small quantity of water. This increases the energy required and exposes the equipment to more abrasive dust. The extraction site also needs a way to transport the water or ice-bearing material back to the habitat. A valuable resource becomes truly useful only when the cost of recovering it does not outweigh the benefit it provides. Water obtained from the moon cannot be poured directly into a drinking glass. It may contain dust, minerals, and other substances that must be removed. After purification, some of the water may enter the habitat's daily supply, while the rest is stored for critical needs. Producing water locally would reduce dependence on Earth, but it would still require the same network of treatment, testing, and storage used for water brought from home. The ability to use materials already available at an exploration site is commonly known as in situ resource utilization. The basic idea is simple. Instead of bringing everything from Earth, humans use some of the materials already present on the Moon to support life. Water is one of the most important targets, but regolith may also be used for shielding, construction, or as a raw material for certain technical processes. In situ resource utilization does not mean that the base immediately becomes independent. Excavation machinery, processing equipment, spare parts, and many initial materials must still be transported from Earth. The crew will need time to learn how to operate these systems in the real lunar environment, where dust, temperature, and gravity are very different from conditions in a laboratory. Even so, every kilogram of material produced on the Moon is 1 kilogram that may not need to be launched from Earth in the future. The value of water also lies in its molecular structure. Each water molecule contains hydrogen and oxygen, two elements that can be separated through a process powered by electricity. Oxygen can support the habitat's atmosphere or other operations, while hydrogen and oxygen may also play roles in energy production and fuel. A deposit of ice hidden in darkness therefore represents more than drinking water. It may become a source of raw material for many different systems. Separating water does not create free energy. The process requires a substantial supply of electricity, and recombining its components to release energy requires the proper equipment. Every stage involves losses and maintenance demands. Yet, the ability to transform a local resource into water, oxygen, or fuel could change the way humans design an entire lunar settlement. If some fuel could be produced on the Moon, vehicles would not need to carry their entire supply from Earth. Because lunar gravity is weaker, launching material from the Moon's surface also requires less energy than launching it from Earth. This means regions containing water ice may serve not only as sources of support for lunar bases, but also as supply points for journeys farther into space in the future. Even so, water at the lunar poles is not a treasure that can be extracted without limit. We still do not fully understand how much ice can be accessed conveniently, or what rate of extraction could remain sustainable over long periods. Some locations also hold great scientific value, because their ice may preserve traces of materials that have reached the Moon over time. Extraction will need to be balanced with research and the protection of these exceptional sites. During the early stages, a base may still need to bring most of its water from Earth while testing small-scale methods of recovery and local extraction. Lunar water might first be used for technical purposes, to build emergency reserves, or to supplement part of the habitat's daily supply. Only as the technology becomes more reliable can dependence on outside sources gradually decline. Self-sufficiency will come through many small steps rather than one complete transformation. Water reserves may also provide an additional layer of protection. Because water can reduce the effects of certain forms of radiation, storage tanks could be positioned around areas requiring greater shielding. In this way, the same resource could support daily life while also becoming part of the protective structure. However, the arrangement must ensure that the water remains easy to access and that a single failure does not destroy both the reserve and the shielding it provides. The base will also need several smaller storage tanks rather than placing all of its water in one large reservoir. If one tank leaks or becomes contaminated, the others can continue supporting life while repairs are made. Pipes need valves that allow individual sections to be isolated, while monitoring systems must detect even very small losses of water. Redundancy is essential because there is no river or water truck waiting outside the door. Water freezing inside pipes can also become a serious problem. If equipment outside the habitat loses heat, the water within it may freeze, expand, and damage the surrounding material. Pipes must therefore be heated, insulated, or emptied when they are not being used. A substance that feels entirely familiar on Earth can become difficult to control amid the Moon's extreme temperature changes. At the other extreme, Liquid water cannot behave in its familiar way if the pressure falls too low. Depending on the conditions, it may rapidly boil, evaporate, or freeze. This means every water processing activity must take place inside carefully controlled, sealed systems. Only when the habitat maintains the proper pressure and temperature can water flow through pipes as it does inside a home on Earth. Preserving water therefore also means keeping air, temperature, and electrical power working together. A water tank cannot be separated from the habitat's other systems. If temperature control fails, the water may freeze. If power is lost, the pumps stop. If pressure changes, the liquid may behave in dangerous ways. Every drop exists within a network where the weakening of a single link can produce many consequences. The people living inside the base will gradually learn to recognize the value of things that once seemed entirely ordinary. The sound of water moving through a pipe will no longer be merely the background noise of daily life. It will mean that the pumps are still running, the filters are still allowing water to pass, and the reserves remain sufficient for that day. A clear glass of water will become the result of an entire chain of machines working behind the walls. In the morning, one crew member finishes a glass of water and places it on the table. That water passes through the body, becomes moisture and wastewater, and is then collected through several different pathways. It moves through filters, is tested and disinfected, and finally enters a storage tank alongside countless other drops. Days later, it may return in another glass. Even though no one can know the exact journey taken by each molecule, the beauty of this system lies in its continuity. No rain falls onto the roof of the habitat, no river carries water down from distant mountains, and no underground spring naturally refills the tanks. Instead, a small cycle is created through human intelligence, machinery, and care. It is not as vast as Earth's water cycle, but it is enough to sustain life within a few rooms on a cold, dry world. Every portion of water successfully recovered extends the habitat's ability to survive. Every amount extracted from lunar ice reduces its dependence on shipments from far away. Yet the system must still be cared for each day, because an artificial cycle cannot protect itself as oceans and clouds do. It continues only when filters are replaced, pipes are inspected, and people remain attentive to the smallest warning signs. In a future settlement, children may grow up with an entirely different understanding of water. They may know exactly which tank their water came from, how many treatment stages it passed through, and why a faucet must never be left running longer than necessary. To them, reusing water will not be an emergency measure, but an ordinary rhythm of life. Every glass will carry the story of the dependence shared between human beings and their habitat. Yet water satisfies only part of what life requires. It can ease thirst, keep the body functioning, and allow technical systems to continue operating. Air can be filtered, oxygen replenished, and waste processed so that some materials return to the cycle. But human beings need more than the things that keep the body biologically alive. After many months inside a sealed habitat, a meal will be judged by more than its energy and nutritional content. A familiar flavor may bring back memories of a kitchen on Earth, while a touch of fresh color may change the mood of the entire crew. Food carries memory, daily rhythm, and the feeling that life still contains more than numbers displayed on a control panel. Inside a room built from metal, plastic, pipes, and artificial light, a single green leaf may become the most extraordinary thing of all. It uses the same water that has been recovered, absorbs carbon dioxide from the air, and grows slowly from one day to the next. Water can be purified and returned to the cycle, but when it passes through the roots of a plant, it also helps create something machines cannot fully replace: the feeling that life is still continuing to grow. Inside a room surrounded by metal, plastic, and artificial light, a young leaf slowly unfolds. Its small patch of green stands out among the pipes, screens, and cold white walls, like a fragment of earth placed somewhere it does not belong. Beyond the habitat may lie the gray surface of the moon or the cold red landscape of Mars, where not a single tree or blade of grass grows naturally. For the people living inside, that leaf becomes the closest thing to a field, a forest, or a garden they once knew. During the first few days, the growing tray is simply another item on the schedule. The crew checks the water supply, adjusts the lighting, and watches to see whether the seeds have begun to sprout. But after weeks spent inside rooms that barely change, the small garden gradually takes on a different meaning. It is no longer only an experiment. It becomes the one place in the habitat where something grows from one day to the next. Food is one of the first things that must be carefully planned for any long journey beyond Earth. The human body needs enough energy to work, exercise, repair equipment, and keep its organs functioning steadily. But a meal is not judged only by the energy or nutrients it contains. Flavor, color, and the experience of sitting down to eat together also directly affect the mood of people living within a confined space. On Earth, when people grow tired of a particular meal, they can change the menu, walk into a store, or visit a different restaurant. During a mission lasting many months, nearly all the food has been selected and packaged before departure. Every package must be lightweight, easy to store, and safe enough to remain edible for a very long time. This gives the crew a stable source of nutrition, but it can also make meals increasingly familiar and monotonous. Packaged foods may be dried, heat-treated, or sealed inside airtight containers to slow spoilage. Some dishes only need to be warmed, while others require water before they can be eaten. The simpler the preparation, the more time, electricity, and washing water can be saved. Yet even with careful preservation, flavor, texture, and certain nutrients may still change after many months. A meal that seemed appealing during the first few weeks may become difficult to eat after appearing too many times. Fatigue and stress can also reduce a crew member's appetite even when the body still needs energy. If this continues, the crew may consume less than they need and gradually lose strength without immediately realizing it. The food system must therefore preserve not only nutrition, but also the desire to eat. Meal times are also among the few moments when the group can look away from their screens and sit together. After hours of work, the small table becomes a place where they share food, talk about a problem that has been solved, or simply sit quietly beside one another. These moments help preserve a familiar daily rhythm within an unfamiliar environment. Sometimes, the greatest value of a meal is not what lies on the plate, but the feeling that everyone is still living together as a small community. This is where fresh food becomes especially meaningful. A few vegetables cut from a growing tray cannot provide enough energy for an entire day, but they can completely change the experience of a packaged meal. The crispness of a leaf, the faint scent of a plant, and the bright green color on the plate offer something that long-lasting stored food struggles to preserve. Even a very small harvest can become an event the entire crew looks forward to. Humans have experimented with growing many kinds of plants in space, from lettuce and radishes to peppers. These studies have shown that plants can still germinate and grow when light, water, and nutrients are carefully controlled. However, the goal is not to turn a few growing trays into a farm capable of feeding the entire crew. Their immediate value lies in providing fresh food and helping researchers understand how plants respond to environments beyond Earth. During Chapia missions, caring for plants is placed alongside activities such as preparing meals, exercising, maintaining equipment, and conducting research. The crew does not spend the entire day tending the garden, because they must also manage a demanding schedule and respond to simulated problems throughout the mission. NASA wants to observe how a plant-growing system fits into the practical rhythm of daily life. If caring for it becomes too complicated, the garden may turn into a burden rather than a source of support. Plants do not know that the person caring for them is busy repairing a pump or responding to an air system warning. Their roots still need water, their leaves still need light, and the temperature must remain within a suitable range. If inspections are delayed for too long, the plants may begin to weaken before the crew returns. The garden is therefore also a test of time management and the ability to maintain responsibilities under pressure. For a single leaf to unfold, many systems must work together. Lamps provide light in place of the sun, pipes carry water to the roots, and the habitat's air contains the carbon dioxide the plants need to grow. Nutrients must be mixed into the water or placed in the growing material in carefully controlled amounts. Even a small change in light, temperature, or humidity can slow the plant's development. Lighting is one of the most energy-intensive parts of a growing system. On Earth, a pot of vegetables can receive free sunlight through a window, but inside a habitat shielded from radiation, light usually has to come from lamps. Those lamps must operate long enough for photosynthesis without producing too much heat. Every hour of illumination uses electricity that is also needed by air filters, water processing systems, and communication equipment. The water delivered to the roots is not entirely new. It may once have been inside a crew member's drinking glass, later becoming moisture in the air or wastewater before being recovered through the filtration system. Once it enters the roots, most of that water eventually escapes through the leaves as vapor. The humidity control system can collect that moisture and return it to the habitat's circulation. In this way, a drop of water may travel from a person to a filter, from the filter to a plant's roots, and from the leaves back into the air. This small cycle connects humans, plants, and machinery within a single system. The garden not only receives resources from the habitat, but also returns moisture and some oxygen. Even so, a few trays of vegetables remain far too small to replace the primary equipment keeping the atmosphere safe. Plants absorb carbon dioxide in the presence of light and release oxygen through photosynthesis. This makes them a natural part of the living environment, but not an oxygen-producing machine that can be switched on whenever needed. When the lights are off, plants continue to respire and use a small amount of oxygen to remain alive. The amount of gas they exchange also changes according to the size, age, and condition of each plant. The garden must therefore be treated as a living system, not simply as a machine for producing food. Machines generally respond according to predictable parameters, while plants may grow differently even when cared for under nearly identical conditions. One may grow quickly, while another beside it develops more slowly or begins showing small spots on its leaves. The crew must notice these signs and identify the cause before the problem spreads. Within a closed environment, harmful fungi or bacteria can move rapidly between growing trays placed close together. High humidity around the leaves creates favorable conditions for their growth, while pesticides must be used sparingly because the air is continuously recycled. The safest approach is often to detect the problem early, isolate the affected plant, and adjust the surrounding conditions. A single discolored leaf may become the first warning for the entire garden. Plant roots also require careful attention. On Earth, excess water can drain deeper into the soil, but in a closed growing system, the amount delivered must be precise. Too little causes the plant to dry out, while too much can deprive the roots of oxygen and weaken them. Sensors help monitor moisture levels, but the crew must still inspect the plants directly, because one faulty sensor could cause an entire tray to receive the wrong amount of water. Many growing systems designed for space do not use garden soil in the familiar way. Roots may be supported by a lightweight material or placed in direct contact with nutrient-rich water. This reduces the mass that must be transported and allows tighter control over what each plant receives. In return, the plants become dependent on pumps, pipes, and electrical power, because even a small failure can leave the entire root system without water in a short time. Lunar regolith and Martian soil cannot simply be collected and used like soil from a garden on Earth. They contain almost no organic matter and may include substances unsuitable for plant growth. If humans want to use local material, it must first be analyzed, treated, and enriched with nutrients. In the earliest bases, most crops will still depend on carefully prepared growing systems brought from Earth. The choice of plants must also be practical. They need to grow quickly, use little space, and produce a large edible portion compared with the water and electricity they consume. Leafy vegetables are often suitable because they can be harvested relatively soon, while crops that produce seeds, roots, or fruit generally require more time. Yet, a settlement hoping to produce most of its own food would need a much wider variety of plants. A few trays of vegetables can provide additional flavor and some nutrition, but they cannot supply enough energy for long-term survival. To meet the crew's full needs, the base would also have to grow crops rich in carbohydrates, protein, and fat. That would require far more space, electricity, water, and labor. The distance between an experimental garden and a true farm therefore remains very large. The first bases will probably combine two sources of food. Stored packages will provide most of the crew's energy and ensure survival if the crops encounter problems. The garden will offer fresh food, greater variety, and opportunities to test methods of local production. This combination is more realistic than making the crew's entire survival depend on a harvest that could fail because of one small pump. Seeds must also be treated as an important reserve. Some are planted for the current crop, while others must be preserved for replanting if the plants die or the harvest fails. They need protection from moisture, excessive heat, and radiation levels that could reduce their ability to germinate. Without healthy seeds, the garden will eventually disappear, even if every piece of equipment continues to function. When the plants grow well, the crew can see the results of their work in a very direct way. Tiny seeds become roots, stems, and new leaves over the course of each week. Unlike a screen that displays only numbers, plants change through shape, color, and scent. Their growth helps people feel the passage of time rather than merely counting the days remaining in the mission. A new leaf may mark the third week, a flower bud may appear the following month, and harvest day can become a milestone everyone remembers. Beyond the window, the landscape may remain almost unchanged for months. Inside the garden, however, every day leaves behind a small sign. The plants become living clocks, measuring time through growth rather than numbers. Caring for plants also creates a kind of quiet, very different from technical work. The person tending them does more than read data. They observe the color of the leaves, touch the growing material, and search for new signs of development. The task calls for patience rather than a rapid response to an alarm. During a day filled with fans, screens, and checklists, a few minutes beside the garden can allow the rhythm of life to slow down. The color green also changes the feeling of the room. It breaks the repetition of white, gray, and metallic surfaces while carrying a subtle scent that no machine can reproduce exactly. A person may not realize how deeply they miss trees and plants until the first leaf unfolds. At that moment, the garden becomes more than a place where food is produced. It becomes part of their memory of Earth. That emotional connection also makes the failure of a crop more painful than the nutritional loss alone would suggest. The crew may have watched every leaf, waited for harvest day, and viewed the garden as a sign that the habitat was stable. If the system fails and the plants wither, the sense of loss may spread through the entire group. Fresh food affects morale in ways that cannot be measured only by the weight of the harvest. Plants also bring a kind of responsibility whose results appear slowly. When the crew repairs a machine, they may know immediately whether it is working again. With crops, a decision made today may not reveal its effects for several days. Too much water, lights placed too close, or a missing nutrient may not trigger an immediate alarm, but the consequences will gradually appear in the leaves that follow. This slow response makes the garden a particularly meaningful image during a long mission. It reminds people that not everything can be repaired by pressing a button or replacing a component. A living system needs time to recover, and it also needs attention before damage becomes obvious. That is true of plants, and sometimes it is also true of the people caring for them. When harvest day arrives, a few leaves are cut from the tray and carried to the table. They may be divided into very small portions and placed beside packaged food the crew has eaten many times before. Yet that meal feels different, because part of it has just been created inside the habitat. The crew is no longer relying only on what was brought from Earth. They have begun producing something new in the place where they now live. It is a small but important step on the path from survival to settlement. A temporary visit can depend entirely on packaged food, but a permanent home must gradually produce water, air, materials, and food locally. The small garden cannot yet sustain human life, but it proves that part of Earth's living world can continue growing beyond our home planet. Every leaf is an experiment for the larger settlements of the future. Outside the habitat, the world remains without trees. There is no wind carrying the scent of grass, no forest casting shade, and no natural spring waiting beyond the cold months. The color green exists only because electricity continues to flow, water continues to be filtered, and people continue to devote time to its care. If one link in that chain stops working for too long, the small garden will quickly remind them that life here has never been natural. At the end of the workday, the lights in the growing area gradually dim, according to their programmed schedule. The leaves rest in the gentle flow of air while sensors continue monitoring water, temperature, and humidity. The crew returns to the living quarters, carrying a few freshly harvested vegetables. or perhaps only a photograph showing that the plants have grown since yesterday. Another day in the mission is marked by one very small change. But the plants are not the only living things that must be watched carefully. The 4 people living beside that garden are also affected by artificial light, demanding schedules, and months of repetition. They may continue completing every assignment on time, speaking normally, and appearing healthy on camera, while changes inside them unfold much more slowly. A garden deprived of light does not wither on the first morning. Its leaves merely become a little paler. Its stems grow more slowly, and the clearest signs often appear only after the problem has continued for some time. The human mind inside a confined environment can change in much the same way. Beyond the leaves that require care, the next challenge lies within 4 people who cannot step outside and find somewhere else to go. 4 people sit around a small table at the end of the day. They have shared hundreds of meals there, seen the same familiar dishes, and heard many stories first told weeks earlier. No one is openly upset, yet the silences have grown longer, and there are fewer new things left to share. Inside a space they cannot leave, even the sound of someone chewing, the way they set down a cup, or their habit of checking the time gradually becomes deeply familiar. The first days of a mission often bring a sense of excitement. The habitat is still new, the work schedule has a clear purpose, and every task feels like part of a larger expedition. The crew members are learning one another's personalities, exploring each corner of their living space, and discovering how to operate the equipment. At that stage, novelty makes the confined environment feel more like an adventure than a place where they will have to live for an entire year. But after many months, every door has been opened thousands of times, and every corridor leads somewhere they know too well. There is no different street to walk down, no new restaurant to visit, and no unfamiliar face appearing during the day. The crew cannot hear natural wind, smell the earth after rain, or step outside simply for a change of atmosphere. Their world gradually contracts into a few rooms and 3 other people who are always nearby. Isolation does not necessarily begin with obvious sadness. Sometimes, it appears in the moment when someone wants to take a walk alone but realizes that every door leads only to another part of the same habitat. A call with family may allow them to hear familiar voices, but it cannot replace the feeling of sitting together in the same room. Life outside continues to change, while the environment surrounding the crew remains almost identical from one day to the next. In a group of only 4 people, every member must take on several roles at once. They are colleagues during working hours, neighbors during their free time, dining companions at every meal, and the first emergency response team whenever equipment fails. The person who has just argued with you about a task may still be the one who must help inspect your suit a few minutes later. No one can choose to meet only during pleasant moments and then return to a completely separate private world. Major conflicts are usually easy to recognize, but small habits are more likely to accumulate quietly. Someone who leaves tools in the wrong place, speaks too loudly while others are resting, or regularly arrives a few minutes late may cause little concern during the first week. After hundreds of repetitions, that very small behavior can become far more irritating than it would normally seem. The problem lies not only in the action itself, but also in the fact that no one has enough distance to temporarily forget it. On Earth, people can reduce stress by going home, spending time with a different group of friends, or walking through the city for a few hours. Inside the habitat, a disagreement can follow them from the work area to the dining table and then back to the sleeping quarters. If the problem remains unresolved, silence itself may become a way of expressing resentment. The ability to clearly explain what one needs and to listen to others therefore does more than make life more comfortable. It is directly connected to safety. A well-coordinated group may notice changes in one another before the person experiencing them does. One crew member may observe that someone is checking the same reading repeatedly, speaking less than usual, or responding slowly when asked a question. These signs do not necessarily indicate a serious problem, but they may suggest that the person is tired or losing concentration. Reassigning part of their workload at the right moment can sometimes prevent a costly mistake. NASA does not simply measure how many assignments the crew completes. Researchers also observe sleep, attention, behavior, health, and the group's ability to cooperate under isolation, limited resources, and heavy workloads. The goal is to understand the changes that occur before they begin to affect safety in obvious ways, allowing work schedules, habitat designs, and support systems to be improved for long-duration missions. Sleep is one of the most important indicators. The human body follows a biological rhythm close to a 24-hour cycle, usually relying on the transition between light and darkness to determine when it should be awake or at rest. Inside the habitat, the lights switch on and off according to an artificial schedule, while the sounds of fans and pumps rarely stop. If the work schedule changes too often, the body's internal clock may no longer align completely with the timetable shown on the screen. One poor night of sleep rarely causes an immediate emergency. But when sleep deprivation continues, people may respond more slowly, overlook details more easily, and find it harder to control their emotions. NASA considers the combination of insufficient sleep, disrupted biological rhythms, and excessive workloads a risk that can reduce performance during long missions. The concern is that a tired person may still feel as though they are working just as accurately as they do every other day. Short attention tests can help reveal declines that participants have not yet noticed themselves. On a screen, they may need to respond when a signal appears, remember information, or complete simple tasks within a limited time. A minor mistake or a slower response is not a failure on its own, but a lasting change may indicate that sleep schedules and workloads need to be adjusted. Objective data allows the group to rely on more than the familiar answer that everything is still fine. Rest time is therefore not an empty space with no value between assignments. If the schedule is too demanding, the body and mind do not have enough time to recover. But if it is too light, monotony can weaken a person's sense of purpose and make the days seem to pass more slowly. A long mission must create a rhythm that keeps everyone busy enough to feel they are moving forward, while still leaving enough space for sleep, exercise, and time alone. Privacy inside the habitat does not necessarily require a large room. Sometimes, it may be nothing more than a closed curtain, a pair of headphones, or a small corner where the others understand that someone should not be disturbed. NASA has noted that as missions become longer, the need for usable space and privacy becomes increasingly important. Saving every square meter may make a spacecraft lighter, but reducing the interior too severely can increase the pressure on the people who must live there for months. Small rituals help the group preserve a sense of stability. They may eat at the same time each day, reserve one evening for watching a movie, or mark the weekend with a different meal. One person may write a few lines before bed, while another tends the plants or exercises on a fixed schedule. These habits do not make the habitat any larger, but they give structure to the days and prevent time from becoming an indistinguishable series of repetitions. Birthdays, holidays, and mission milestones also take on greater meaning than usual. A saved meal, a few photographs from family, or a message arriving at the right moment may become an event anticipated for weeks. These moments divide a long year into smaller stages that are easier to understand and endure. People do not simply count the days that have passed. They also remember what happened during each part of the journey. Communication with family helps reduce the sense of distance, but it also brings pressures of its own. A crew member may receive news about changes back home while being unable to be there in person or offer any direct help. Too little information can leave them feeling disconnected, while too many problems from outside may interfere with concentration. The crew and support team must find a balance between maintaining connection and protecting the ability to work inside the habitat. Different personalities within the group can be both a source of strength and a cause of friction. A careful person may notice small errors, but can sometimes make others feel that they are being checked too closely. Someone decisive can be valuable during an emergency, yet may become overbearing if they always insist on making every decision. The goal is not to select 4 identical people, but to build a team that knows when to lead, when to listen, and when to defer to someone else's expertise. During an emergency, the way the group communicates becomes especially important. If an alarm sounds and all 4 people begin giving instructions at once, the small room can quickly become chaotic. The team must know who will examine the data, who will work on the equipment, who will monitor the effects on other systems, and who will communicate with mission control. Roles practiced in advance allow them to respond quickly without arguing, while valuable time is passing. When the emergency ends, the pressure does not disappear the moment the alarm falls silent. One person may continue thinking about the mistake that occurred, while another may feel that their concerns were ignored. Reviewing the event together helps separate the technical problem from personal emotions and reveals what needs to change. If the group simply returns to the schedule without discussion, unresolved tension may reappear in an entirely different disagreement several days later. Monotony can also make unusual conditions harder to notice. When a control panel displays the same stable readings for months, people may begin glancing at it without truly reading the information. A very small change can be missed because the brain has grown accustomed to assuming that everything is normal. Cross-checking between two crew members helps reduce this risk, because safety does not depend on no one ever making a mistake. It depends on mistakes being discovered before they become dangerous. Constant noise is another part of life inside a sealed habitat. Fans, pumps, and climate control systems must run day and night to maintain the air and temperature, so complete silence almost never exists. The crew must learn the habitat's normal sounds in order to recognize when a machine begins vibrating or producing an unfamiliar noise. At the same time, continuous mechanical sound must be kept low enough that it does not interfere with sleep or concentration. Smell can also become a signal. Because the air is constantly filtered and recirculated, odors from food, clothing, and materials may remain in the room longer. An unfamiliar smell may come only from dinner, but it could also indicate overheated wiring, standing water, or a problem with a filter. Inside a sealed habitat, ordinary human senses become an additional layer, supporting the electronic sensors. Not every day of the mission will go well. On some days, the group completes its work on time and shares a relaxed meal. On others, one person sleeps poorly, another loses patience, and a small error delays the entire schedule. The goal is not to remain in a perfect state for an entire year, because that would be nearly impossible. What matters is the group's ability to recognize a difficult day and return to a stable rhythm before it continues for too long. An adjusted rest period, a task transferred to someone else, or a brief conversation may prevent pressure from accumulating. These measures do not appear as sophisticated as space technology, but they have a direct influence on safety. Human beings are not machines that can operate forever at the same level of output. Knowing when to reduce the workload is also part of survival. Trust is built through small actions repeated every day. A person who keeps their word, returns tools to the correct place, and admits when they do not understand something helps the entire group work more safely. If someone hides a mistake because they are afraid of being blamed, the habitat may lose the opportunity to address the problem early. A strong team is not one that never makes mistakes, but one whose members trust each other enough to report them before consequences appear. Simulated missions, such as Hera, allow NASA to observe these changes without first sending people away from Earth. Participants live in a sealed environment, perform technical work, and experience intentionally created communication delays. During some Hera campaigns, the simulated delay can increase to around 5 minutes as the crew approaches Mars. These periods of waiting force the group to coordinate independently instead of asking mission control about every small decision. However, the participants in Houston still know that in a serious emergency, the door can be opened and help will arrive. On the Moon or Mars, that knowledge no longer exists in the same way. There is no hospital at the end of the corridor, and no repair team that can enter within a few minutes. The understanding that there is no quick way out gives trust between crew members far greater weight. On the Moon, a signal takes only a little more than a second to travel from the surface to Earth. A conversation still contains brief pauses, but a voice from mission control can return within a few seconds. The crew must handle immediate situations on their own, yet they can still feel that someone back home is listening almost in real time. The great distance involved in rescue has not yet become an equally great distance in conversation. On Mars, the rhythm of communication will change completely. A question sent to Earth cannot receive an immediate answer, even when the communication system is working perfectly. The 4 people inside the habitat will then be more than colleagues and neighbors. They will also be one another's nearest technical team, medical team, and source of emotional support. Every habit of cooperation developed through months of living together will be tested during those periods of waiting. A crew member sends data toward Earth and looks at the silent screen. There is no failure in the connection, and mission control is still listening on the other side of space. But the reply cannot arrive yet, simply because even light needs time to cross the distance between the two planets. From that moment on, isolation is no longer contained only within the walls. It begins to be measured by the number of minutes in which human beings must make decisions on their own. An unexpected warning appears on the screen in the middle of a work shift. A sensor shows that the temperature inside the technical compartment is rising, while one crew member begins to notice a faint smell of something burning. They send all the data to Earth, describe the situation, and ask which system should be shut down first. Then the room falls silent, not because the connection has been lost, but because the answer is still traveling across millions of kilometers of space. On Earth, a phone call takes place almost instantly. The person on the other end can hear a question, think about it, and respond within the natural rhythm of a conversation. But signals traveling between planets cannot arrive the moment they are sent. Radio waves move at the speed of light, fast enough to circle Earth many times in a single second. Yet even that speed begins to feel slow across the distance between Earth and Mars. The two planets do not remain still beside one another. They are constantly moving around the Sun along different orbits. At certain times, they are relatively close, while at others, they are separated by a much greater distance, sometimes with the Sun lying almost directly between them. As the distance changes, so does the time required for a signal to travel. Under favorable conditions, a message takes about 4 minutes to reach Mars from Earth. When the planets are farther apart, the journey may take around 24 minutes. This means that a complete question and answer exchange may require anywhere from roughly 8 minutes to nearly 48 minutes, even before accounting for the time people on Earth need to read the data, discuss the situation, and choose a response. If the problem is complicated, the reply may arrive even later. During that waiting period, the equipment continues to heat up, the air continues to circulate, and conditions inside the habitat may continue to change. The crew cannot remain still simply because mission control has not yet responded. Consider again the faint burning smell inside the technical compartment. After sending their question, the crew checks the electrical diagrams, compares readings from different sensors, and identifies which equipment has recently changed state. If they wait nearly an hour for instructions, an overheated wire may already have damaged nearby components or allowed smoke to spread through the ventilation system. The people living on Mars must therefore be capable of isolating the affected area, disconnecting the appropriate power supply, and protecting the habitat before advice from Earth arrives. Distance does more than slow down a conversation. It transfers part of the responsibility from mission control to the people living inside the habitat. Earth can still provide expertise, analyze data, and support long-term decisions, but it cannot manage every second of an emergency. When a problem demands immediate action, the crew on Mars must become their own nearest mission control. This creates a clear distinction between communication and control. Communication can still take place through text, audio, images, and technical data packages. Mission control can send work schedules, repair instructions, or analytical results that the crew does not have the tools to produce on its own. But direct control, in which someone on Earth watches events unfold and gives instructions for every movement, is nearly impossible for tasks requiring a rapid response. On the Moon, the one-way delay is only a little more than a second, so an operator on Earth can still monitor equipment with brief pauses. On Mars, no one can use a joystick to drive a rover while watching a live camera feed in the usual way. By the time an image of a rock reaches Earth, the rover may already have traveled much farther if it has continued moving. Every vehicle must be able to stop, avoid obstacles, or independently carry out part of a plan sent in advance. This is why robots on Mars are not controlled like toy cars. Teams on Earth usually send a carefully prepared sequence of tasks, and the robot then carries them out using its own automated systems. It must recognize terrain, evaluate safety, and stop when conditions become uncertain. Humans still decide the objective, but every small movement cannot wait for approval from another planet. With a human crew on Mars, Robots could be used more flexibly, because the people operating them would be much closer than mission control on Earth. They could send robots to examine hazardous areas, transport equipment, or inspect places that are difficult to reach in a protective suit. Even then, however, the machines would still need to protect themselves if communication were interrupted for several minutes. The relationship between humans and robots would resemble cooperation more than a sequence of commands for every movement. This is also why simulated missions have crews perform excursions, operate rovers, and work at locations beyond the main habitat. NASA wants to observe how responsibility is divided among the people outside, the crew members monitoring them from within the base, and the support team far away. If every question must be sent to Earth, the work will proceed too slowly. But if the crew makes every decision without sharing data, they may lose the experience and perspective offered by the support team. The balance lies in determining which decisions must be made immediately and which can wait. A suit losing pressure requires an instant response, while choosing a survey location for the following week can be discussed with Earth. Sudden pain must be evaluated on site, while test results may be sent home for deeper analysis by physicians. The crew must learn to classify each problem before deciding whether it is safe to wait for a reply. Medicine is one area where communication delay creates particular pressure. Earth can provide guidance and connect the crew with highly experienced doctors, but those doctors cannot physically examine the patient or respond instantly as the condition changes. Crew members must be trained to perform initial assessments, use diagnostic equipment, and manage common emergencies. They also need support systems that help them locate the correct procedure without waiting through an exchange lasting tens of minutes. A crew member injured while working outside the habitat cannot simply lie still and wait for Earth to respond. The others must inspect the suit, stabilize the person's condition, and return them to safety using skills they have already practiced. Medical data can then be transmitted for further guidance. In such a situation, knowledge from Earth remains extremely valuable, but the first critical minutes always belong to the people already present on Mars. The delay also changes the rhythm of daily communication. A conversation no longer unfolds through naturally connected sentences, but begins to resemble an exchange of letters recorded in sound and images. Someone records a message, sends it, and continues with another task while waiting for a reply. By the time the response arrives, their mood or circumstances may already have changed from the moment the question was asked. Communication with family therefore takes on a different feeling as well. A crew member may describe the day, ask about their children, and then wait many minutes before hearing an answer. No one can interrupt to laugh at the same moment or react immediately to an unexpected story. The connection remains, but it loses the sense of immediate presence that human beings usually take for granted. The crew can adapt by sending longer messages, telling a complete story, or recording images from their day. Their families on Earth can respond in the same way, almost as though the two sides are exchanging brief journals. This form of communication is not entirely cold or distant, but it requires patience. The waiting becomes a normal part of every relationship stretched between two planets. During work, some of that waiting can be reduced by sending complete information from the beginning. Instead of asking a short question and then waiting for Earth to request more data, the crew needs to include images, measurements, and the steps they have already taken in a single package. Mission Control must also respond with several possible options, clearly explaining which conditions apply to each one. Every message must be detailed enough to avoid another exchange that could take nearly an hour. This makes careful documentation especially important. If the data is missing even one critical detail, the team on Earth may not have enough information to offer useful guidance. But when they send a request for clarification, that message must travel several minutes to Mars, and the reply must take a similar amount of time to return. A single missing detail can stretch a problem-solving process from a few minutes into several hours. Automated systems can help by gathering relevant data before a message is sent. When an alarm appears, the computer can attach temperature, pressure, power consumption, and the operating history of the affected equipment. The crew does not have to remember every measurement during a stressful moment, and the team on Earth receives a more complete picture. Human beings must still describe what the sensors cannot easily detect. However, such as a burning smell, an unusual vibration, or the sense that a machine is behaving differently than usual. The intelligence of the habitat therefore exists not only within its computers, but also within the experience of the people living there. A crew member who has heard the same pump running every day for months may notice a change before a sensor issues a warning. Someone else may spot a small patch of moisture or feel that the airflow is weaker than normal. These details allow the group to act immediately, rather than waiting for a distant system to confirm what is already happening in front of them. Autonomy does not mean that the crew becomes disconnected from Earth. Mission Control still monitors the overall condition of the base, identifies long-term trends, and provides knowledge from hundreds of specialists. A team of 4 cannot carry the combined experience of every physician, engineer, and scientist. The strength of the mission lies in combining rapid decisions made on site with deeper analysis performed from far away. But this division of responsibility also requires trust. Earth must trust the crew to change the plan when actual conditions no longer match what was expected. The crew must also trust that instructions from Mission Control are based on complete data, even though the people sending them cannot directly see the habitat. If the two sides do not clearly understand one another's authority, distance can turn every decision into a prolonged argument. A simulated mission helps reveal these uncertainties before humans actually travel to Mars. When communication delays are introduced deliberately, the crew cannot ask Mission Control about every minor step. They must organize their own work, handle familiar situations independently, and send only the problems that require deeper assistance. Researchers can then identify where the crew needs greater decision-making authority and where clearer guidance is still necessary. The way procedures are written must also change. A document on Earth may assume that the person following it can always call an expert when something becomes unclear. On Mars, the instructions must be detailed enough for the crew to continue working while waiting for a response. Images, diagrams, and inspection steps must be prepared in advance, while also allowing people to stop safely when actual conditions differ from what was expected. The habitat's local database must contain far more knowledge than a vehicle operating close to Earth. Technical manuals, medical references, equipment diagrams, and repair histories all need to be stored on site. If the connection is temporarily interrupted, the crew must still be able to find the information they need. Mars cannot become a permanent home if every answer exists only inside computers on Earth. At certain times, communication becomes more difficult than the ordinary delay alone would suggest. When the position of the Sun creates strong interference along the path between the two planets, data transmission may be limited for a period of time. Spacecraft on Mars usually operate more cautiously during these intervals and avoid receiving complex commands. For a crewed base, plans for these periods must be prepared in advance so that the team can continue working safely with less direct support. Even then, the silence between the planets does not mean that the crew is completely alone. They still receive data, plans, and personal messages, but everything arrives later. The greatest change lies in how people think about time. A question no longer begins an immediate conversation. Instead, it starts a process that may continue for nearly an hour before the first exchange is complete. When the warning appears inside the technical compartment, the crew does not stare at the screen and wait for a voice from Earth to tell them what to do. They examine the data, divide their responsibilities, and isolate the suspected equipment while transmitting all available information back home. By the time the response arrives, the burning smell may have disappeared, the temperature may have stabilized, and the habitat may already be investigating the cause. Earth's reply then helps confirm the crew's decisions and prepare the next stage of repairs. Distance has changed the roles of both sides. Earth is no longer holding the controls during every situation, but has become a distant source of deep knowledge. The crew no longer simply follows instructions. They must observe, evaluate, and accept responsibility for the most critical opening minutes. This is the level of autonomy required before any settlement can survive beyond humanity's home planet. But before a group of people can make decisions for themselves on the surface of Mars, they must first reach it. The same distance that creates the communication delay is also the vast expanse a spacecraft must cross during a journey lasting many months. The crew will live inside a small vehicle, carrying water, food, and every essential piece of equipment, while Earth gradually becomes a point of light behind them. Compared with that journey, the Apollo missions to the moon were little more than a very short step. Apollo astronauts could reach the vicinity of the moon in about 3 days, while a flight to Mars is usually measured in months. Before seeing a red sunrise on another world, human beings must cross a distance long enough for every challenge of isolation, limited resources, and autonomy to emerge together inside a vehicle, moving through the emptiness of space. The sun slowly rises above a red horizon. Pale light spreads across the dusty plain, touching cold rocks and the outer walls of the habitat. Inside, the clock marks the beginning of a new morning that feels almost like one on Earth, because a Martian day is only about 39 minutes longer than our own. Yet the person standing before the door cannot simply open it and step into the sunrise. A day on Mars is commonly called a sol, lasting approximately 24 hours, 39 minutes, and 35 seconds. This rhythm is close enough to Earth's that people can still wake, work, and sleep according to a familiar schedule. However, the additional 39 minutes each day would gradually shift their routine if the habitat tried to follow the 24-hour clock of home. Life here must therefore be organized according to the red planet's own rhythm. Mars also has seasons because its rotational axis is tilted at an angle similar to Earth's. But a Martian year lasts nearly 687 Earth days, making each season considerably longer. A crew living on the surface for more than a year might still not experience all 4 seasons. The daily clock may feel familiar, but the calendar moves at a much slower pace. The planet also has thin clouds, polar ice, mountains, valleys, and immense plains. Olympus Mons rises higher than any mountain on Earth, while the Valles Marineris Canyon system stretches across a vast portion of the surface. These landscapes make Mars seem like a world that can be explored on foot and by rover, rather than a gaseous planet with nowhere to stand. These familiar features are part of the reason Mars so often appears in humanity's dreams of settlement. It has solid ground, a day and night cycle close to our own, and regions containing water ice. From a distance, the red planet may seem like a colder, drier version of Earth. But once humans place a habitat on its surface, the similarities quickly begin to disappear. Before seeing a Martian sunrise, the crew must first survive a journey lasting many months. NASA estimates that reaching the red planet using current mission concepts could take roughly 7 to 10 months, while many robotic spacecraft have spent around 200 days in interplanetary flight. Throughout that journey, the crew lives inside a small vehicle with no ability to turn back quickly if a critical system develops a problem. When the spacecraft finally enters the Martian atmosphere, the journey is still not truly over. The atmosphere is too thin to slow a large vehicle as easily as Earth's atmosphere can, yet thick enough to generate heat and drag as the spacecraft descends. Those on board must pass through a complex landing sequence before the landing gear can touch the ground. Only then can they begin the life for which they have prepared over many years. Stepping onto Mars is nothing like leaving an airplane after a long flight. Outside, the spacecraft is an environment containing almost nothing the human body can use directly. The air is unbreathable, the pressure is far too low, the temperatures are extreme, and radiation levels are much higher than on Earth's surface. Each person remains alive only because of the suit surrounding their body or the habitat prepared in advance. The Martian atmosphere is composed mostly of carbon dioxide, which makes up about 95% of its gases. Oxygen exists only in trace amounts, nowhere near enough to support a human breath. Even if the carbon dioxide could be filtered out, the atmosphere would still be far too thin for the lungs to function normally. A person could not simply wear an oxygen mask and walk outside as they might while climbing a high mountain on Earth. Average surface pressure is less than 1% of the pressure humans are accustomed to on Earth. Under such low pressure, liquid water is not stable on the surface in the way we normally see it. Depending on the conditions, it may rapidly freeze or evaporate. The human body also cannot maintain the balance it needs if exposed directly to this environment. The suit and habitat must therefore create an artificial layer of pressure between the crew and the world outside. The habitat door on Mars does more than block dust or preserve warmth. It forms the boundary between two completely different environments. On one side is air with sufficient pressure, a stable temperature, and water flowing through pipes. On the other is an atmosphere of carbon dioxide so thin that it cannot protect a person standing only a few steps from the safety of the room. Temperatures on Mars can vary dramatically depending on the time and location. Near the equator, there are afternoons when the ground receives enough sunlight to become relatively warm, but that heat can disappear quickly as the sun lowers. Under the coldest conditions, temperatures may fall to around -153 degrees Celsius. The planet-wide average remains far below anything in which humans could live directly. Because the atmosphere is so thin, it cannot retain and distribute heat as effectively as the air on Earth. Sunlit ground may become considerably warmer than the atmosphere immediately above it, creating conditions that could feel like spring near the feet and winter around the rest of the body. When night arrives, the limited heat quickly escapes into space. The habitat must continue preserving warmth even after an afternoon that seemed relatively mild. Heating systems do more than keep the crew comfortable. They protect water pipes, batteries, electronics, and other components that may fail when temperatures fall too low. If an exterior pipe loses heat, the water inside may freeze and damage the material. A seemingly minor failure during the cold night could affect the water supply or the ability to generate power the following morning. Martian gravity is about 38% as strong as Earth's. A person would feel lighter, find it easier to lift an object, and walk with a different rhythm than at home. Yet objects retain the same mass and inertia, so a large piece of equipment remains difficult to stop once it begins moving. Feeling lighter does not mean that every task becomes safe or simple. Low gravity also raises questions about long-term health. After spending many months in near weightlessness during the journey, the crew arrives on a world with slightly more than 1/3 of Earth's gravity. Their muscles and bones must adapt once again before they begin demanding work on the surface. Humans have never lived for years under this level of gravity, so the long-term effects still need to be studied. Exercise, therefore, remains a necessary part of daily life inside the habitat. The crew must preserve enough strength to wear protective suits, transport equipment, and respond during emergencies. After a long stay on Mars, their bodies must also remain strong enough to endure Earth's gravity again if they return home. Standing securely on the red planet is only one stage of the body's continuing adaptation. One of the most distinctive features of Mars is its dust. Fine particles containing iron-rich minerals give the surface and sky their familiar reddish-orange color. Winds can lift this dust into the air, forming small, swirling columns or developing into regional storms. In some cases, the dusty veil may spread across much of the planet and remain for weeks or even months. Martian winds can sometimes reach high speeds, but because the atmosphere is so thin, they exert far less force than a storm moving at the same speed on Earth. An astronaut would be unlikely to be swept from the ground as shown in dramatic films. The real danger comes from the fine dust that can block sunlight, coat equipment, and enter surfaces that must remain clean. It does not need enough force to knock a person down in order to become dangerous. When dust covers the sky, less sunlight reaches the solar panels. A base that depends too heavily on solar power may need to reduce non-essential activities and draw from stored energy. NASA considers prolonged dust storms one reason to investigate more stable sources of electricity, including nuclear fission. Power must continue flowing even when the red sky becomes a dim veil that lasts for days. In 2018, a planet-wide dust storm blocked sunlight for an extended period and contributed to the end of the Opportunity rover's mission after nearly 15 years of operation. A crewed base would be larger, have more power sources, and offer better maintenance capabilities than a robotic rover, but the lesson remains clear. On Mars, weather does not need to destroy equipment directly. Cutting off enough energy for long enough can create a crisis on its own. Dust also settles on windows, suits, joints, and heat dissipation systems. After every excursion outside the habitat, the crew must clean the equipment before bringing it into the living area. If particles enter the interior, they may affect air quality and gradually wear down materials. The struggle to keep dust outside the door, first encountered on the Moon, will continue on Mars, but here the wind can carry it across much greater distances. The thin atmosphere creates another danger that cannot be seen with the naked eye. Mars today has no global magnetic field like Earth's. while its atmosphere is too thin to block most of the high-energy particles arriving from the sun and deep space. The surface therefore provides only limited protection from radiation. This must be considered in every part of daily life. Not only when the crew steps outside, the habitat may be covered with Martian soil, placed partly beneath the surface, or built with shelters protected by thicker shielding. Water, stored materials, and other protective layers may also be arranged around critical areas. When the sun releases a powerful burst of energetic particles, the crew may need to leave the less protected sections and remain inside the shelter until the danger has passed. Radiation also affects how work is organized. Time spent outside must be monitored, and each crew member's accumulated dose must be recorded throughout the mission. A brief excursion to repair equipment may be acceptable, but thousands of hours of exposure accumulated over many years are a different matter. A true settlement must protect not only the first crew, but also those who may live there for a very long time. Although the surface is cold and dry today, Mars once had a very different past. Valleys, plains, and layers of rock show that liquid water flowed across the planet during ancient periods. The world before the crew is therefore not a place where water never existed, but a planet that lost most of the conditions that once allowed water to remain on its surface. The traces of that past still lie within the rocks, but the habitat must survive under the climate of the present. Today, some of Mars's water remains frozen at the poles and beneath the surface in many regions. Maps created by orbiting spacecraft have identified places where ice may lie relatively close to the ground, helping scientists consider possible landing sites for human missions. A base located near accessible ice would have a better chance of reducing the amount of water that must be brought from Earth. But choosing a site is not simply a matter of finding the place with the most ice. Regions too close to the poles may be colder and receive less sunlight, while steep terrain can make landing and transportation more difficult. A settlement must balance many factors: accessible water, sufficient light, relatively safe terrain, and reliable communication. A good location must support both human life and the operation of machinery. Ice extracted from beneath the ground could be melted and purified for drinking, plant growth, or technical processes. Water could also be separated into hydrogen and oxygen, supporting fuel production and the habitat's atmosphere. Yet, every step requires excavation machinery, electrical power, processing equipment, and spare parts. Detecting ice does not automatically place a glass of water on the dining table. Mars also offers another resource directly within its atmosphere. The MOXIE instrument aboard the Perseverance rover tested a process that drew carbon dioxide from the Martian air and separated it to produce oxygen. During its operation, the device successfully completed this process 16 times, demonstrating that humans could produce some oxygen on Mars instead of transporting all of it from Earth. MOXIE was only a small experiment, not a machine capable of supplying an entire base with breathable air. A system designed to support people and produce enough oxygen for a return vehicle would need to be far larger, operate continuously, and store its output over long periods. Even so, the experiment marked an important step. The unbreathable Martian atmosphere could still become a raw material for life and for the journey home. This changes the way humans may view the red planet. Carbon dioxide is not only something that must remain outside the habitat, it can also be drawn into a machine and converted into some of the oxygen the crew needs. Ice beneath the ground is not merely a remnant of an ancient climate, but a possible source of drinking water and useful material. Settlement begins when the surrounding environment is no longer treated only as a threat, but gradually becomes part of what sustains the base. However, these systems must already be working before the crew arrives. No one would want to reach Mars, only to discover that the oxygen generator cannot tolerate the dust, or that the ice extraction equipment consumes too much electricity. Many mission concepts may require robots to land first, prepare the habitat, inspect water resources, and produce part of the necessary supply in advance. Humans should begin the journey only after the base has shown that it can remain alive before the people who will live inside it ever arrive. Distance makes every failure more serious. If an oxygen production system develops a problem on the Moon, an emergency shipment would still be extremely difficult, but it might arrive within days after being prepared and launched. On Mars, no rescue vehicle can appear quickly. The crew must have enough backup equipment, stored supplies, and repair capability to survive for many months. The return journey also cannot begin at any moment simply because one crew member wants to leave. Earth and Mars are constantly changing positions, so a spacecraft must depart according to a carefully calculated orbital schedule. A small problem inside the habitat may be manageable, but a major emergency cannot always be solved by closing the door and flying home. Mars requires humans to prepare to stay, not merely to arrive. Throughout the months spent on the surface, signals to Earth will still take anywhere from several minutes to more than 20 minutes in each direction. The crew must make its own decisions when equipment fails, when someone is injured, or when a dust storm reduces the power supply. Mission Control will continue providing knowledge and plans, but it cannot respond second by second. Distance turns the habitat into a small world responsible for its own most critical moments. Inside the living quarters, a day still begins, much as it does at home. The lights come on, the crew wakes, checks the systems, exercises, and prepares breakfast. Beyond the window, the sun crosses the sky on a rhythm close to 24 hours. Familiar enough that the body does not lose its sense of time completely. But everything behind that clock is different. The air cannot be breathed, gravity is weaker, dust can linger, and the distance makes a rapid return impossible. Perhaps this is what makes Mars both compelling and dangerous. It resembles Earth enough for humans to imagine living there, yet differs enough that every ordinary need must be recreated through technology. A morning may begin at a familiar hour, but the first breath still passes through a filtration system. A glass of water may rest on the table, but it has been extracted, recycled, or carried across millions of kilometers. Setting foot on Mars would be a tremendous achievement. Surviving a cold season, a dust storm, and hundreds of days of isolation would be an even greater one. But a base that operates only on supplies delivered from Earth is not yet a settlement. It remains a spacecraft resting on the ground, waiting for the next shipment. A place truly becomes a home only when people can repair aging equipment, produce some of their own water and oxygen, maintain their food supply, care for the sick, and continue living when a shipment from Earth arrives late. It must function not only on days when every system performs perfectly, but also when dust covers the solar panels, a pump fails, and the first people who built the base are no longer there to operate it. Mars has a clock much like our own, but settlement will not be determined by the length of its day. It will be determined by humanity's ability to transform a fragile habitat into an environment capable of enduring for many years. Touching down on the red planet will mark the moment humans arrive. Building a sustainable life there will mark the moment they truly remain. A small base stands in the middle of a barren landscape, where beyond its walls there is only darkness, rock, and a layer of dust that is almost never washed away by rain. Inside, the lights remain on, water continues flowing through the pipes, and leaves keep growing beneath artificial illumination. Each morning, people wake according to a schedule that has become familiar, checking the air, the power supply, and the amount of water remaining. From the outside, the place may resemble a home, but to truly become one, it must do more than keep a few people alive. There is a vast difference between visiting, surviving, and settling. A visit may last only a few days or weeks, with nearly all food, water, oxygen, and equipment prepared in advance. The crew needs only to use those supplies long enough to complete the mission and return home. If a device develops a problem, they may be able to leave it behind if another option remains available, or simply wait until the flight is over. A long-term base does not have that simplicity. The people living inside must reuse water, clean the air, maintain the power supply, and repair equipment that has already operated for thousands of hours. They do not merely calculate how much food they need for the coming week, but whether the supply will last for many months. Every filter, pump, and joint becomes part of everyday life, much like the roof, plumbing, and electrical system of a city on Earth. Yet even a base capable of operating for several years may not be a true settlement. A place moves closer to becoming one only when it can continue to exist. If a supply mission arrives late, the original equipment has grown old, and the first people who built it are no longer directly operating every system. Knowledge must be passed on, components must be replaced, and new generations of residents must be able to understand the base without depending entirely on specialists back on Earth. The settlement must do more than survive today. It must prepare for days no one has yet experienced. Electrical power is the first foundation of stability. Without it, the lights go dark, pumps stop running, and the air filtration system can no longer remove carbon dioxide from the living quarters. Water may remain in storage, but it cannot move through the pipes, while the sealed rooms begin to change in temperature. Beyond Earth, a power failure is not merely an inconvenience. It gradually strips the base of its ability to sustain life. Solar panels can generate electricity when lighting conditions are favorable, but a settlement cannot simply hope that the sky will always remain clear and every surface will stay clean. Dust can reduce efficiency. Prolonged darkness can prevent power generation, and a single failed component may disable an entire array. Energy must therefore be stored and distributed through several different pathways, with backup sources reserved for critical systems. The lighting in the growing area may be reduced, but air filtration and medical equipment cannot be allowed to stop. A sustainable base must also know exactly where its electricity is being used and which demands can be temporarily reduced. When the available supply declines, the system must prioritize air, temperature control, water, and communication over less urgent activities. The crew needs to watch the remaining energy as carefully as sailors monitor fuel in the middle of the ocean. Not every device can remain switched on simply because it is present inside the base. Water and air must move through cycles that are almost completely closed. A drop of water is consumed, passes through the body, and becomes moisture or wastewater before being collected and purified again. Carbon dioxide from human breath must be removed, while oxygen is replenished in carefully controlled amounts. The more efficient each cycle becomes, the less the base must depend on shipments from Earth. However, no system can recover everything forever without some loss. A portion of the water remains trapped in waste, filters, or used materials, while small amounts of air may escape during door openings or through extremely slow leaks. Over many months, losses that once seemed insignificant can add up to a substantial amount. A settlement must therefore recycle resources efficiently, while also producing some of them from the surrounding environment. On the Moon, ice within permanently shadowed regions near the poles may provide part of the water supply if humans can develop a reliable way to extract it. Regolith could be used as shielding or as material for certain structures instead of transporting every building block from Earth. On Mars, subsurface ice and carbon dioxide from the atmosphere could become raw materials for water, oxygen, and fuel. Every resource produced locally reduces some of the mass that must be launched across millions of kilometers. But resource extraction does not begin and end with finding a layer of ice. Excavation machinery must operate amid dust and extreme temperatures, while the collected material must be transported, heated, filtered, and tested before use. Those machines need electricity, spare parts, and people capable of repairing them. A source of water beneath the ground becomes truly valuable only when the base can deliver it steadily into a storage tank. The ability to make repairs is therefore one of the clearest boundaries between a temporary base and a place that can truly be called home. On a short mission, the crew may bring complete backup systems, but as the years pass, it becomes impossible to store a duplicate of every pump, robotic arm, and filter. The settlement needs a supply of common components, fabrication tools, and the ability to produce certain parts on site. Printing and machining systems could help turn raw materials into simple pieces such as brackets, connectors, or protective housings. They cannot yet replace every sophisticated component, but they may reduce the number of times the base must stop operating because one small part has broken. Sometimes, survival does not depend on a massive machine, but on a gasket, a screw, or a section of pipe that no longer fits correctly. The ability to produce the right part at the right moment may be more valuable than an entire warehouse filled with equipment that does not match the problem. Repairability also requires machinery to be designed differently from much of the equipment commonly used on Earth. A device that is too tightly sealed, too complicated, or accessible only with specialized tools becomes a burden when it is far from the manufacturer. Components need to be easy to reach, inspect, and replace individually instead of forcing the crew to discard an entire system. A long-term base must be built on the assumption that everything will eventually grow old. Robots can take on some of the heaviest and most dangerous work. They may inspect exterior pipelines, transport regolith, clean solar panels, or enter unexplored areas before humans do. Under harsh conditions of radiation, extreme temperature, and dust, a damaged robot is still far less dangerous than an injured astronaut. But robots do not eliminate the need for repairs, because they also have wheels, joints, and electronic systems that will wear down over time. A well-designed system does not simply have many robots. It assigns them the right kinds of work. Repetitive, physically demanding tasks, especially those performed outside the habitat for long periods, should be given to machines whenever possible. Humans can focus on decisions, unexpected problems, and tasks requiring greater flexibility. This partnership reduces the crew's exposure to radiation and limits the amount of dust carried back into the living quarters. The landing site must also be treated as part of the settlement, not merely as an empty stretch of ground where spacecraft touch down. Engine exhaust can blast dust and fragments of rock towards solar panels, windows, and equipment located far away. If every delivery covers the base in another layer of dust, resupply itself becomes a source of danger. Landing pads must therefore be placed at a safe distance, reinforced to reduce erosion, and connected to the habitat by secure routes. Roads and pathways allow robots and people to transport supplies without constantly disturbing loose dust. Communication systems must cover outdoor work areas and maintain contact even when the terrain blocks a direct signal. These structures may seem less impressive than rockets or crude habitats, but together they form the infrastructure, the quiet foundation that allows every other activity to continue reliably. A place with only a shelter, but no roads, power network, or communication system, is not yet a settlement. Radiation forces humans to think differently about the shape of their homes. The earliest bases may not have wide glass domes looking out across the horizon as they often do in science fiction. The safest living areas may lie beneath layers of rock and soil, behind water tanks, or inside structures covered with regolith. There may be fewer windows, with most views of the landscape provided through cameras in exchange for thicker protection. A dedicated shelter will also be needed for periods when radiation from the sun rises sharply. It may be smaller than the main living quarters, but surrounded by water, supplies, and thick layers of shielding. When a warning arrives, the crew will move inside with communication equipment, medical supplies, and other essentials. The safest room in the base may not be the most beautiful one, but a discreet space hidden deep behind several protective layers. Medical care is another limit that a settlement must confront. A large hospital cannot be built during the earliest stages, yet the base still needs the ability to treat injuries, infections, dental problems, and common emergencies. Crew members must receive training beyond their primary specialties, while medical equipment should support diagnosis and guide them through complicated procedures. On Mars, a doctor on Earth may offer advice, but cannot stand beside the patient. Medicines and medical supplies also have limited shelf lives. A long-term settlement must know which items can be stored for many years, which need regular replacement, and whether some supplies can eventually be produced locally. Even something as ordinary as a toothache can reduce a person's ability to work if it is not treated in time. Long-term survival requires more than preventing great disasters. It must also address the ordinary discomforts and illnesses of the human body. Health also depends on preserving muscle, bone, and a stable daily rhythm in low gravity. The exercise area must be used every day. Food must provide adequate nutrition, and sleep must be protected from noise and excessive workloads. A settlement cannot be called sustainable if people remain alive while their bodies gradually weaken year after year. The goal is not merely to keep the heart beating, but to keep people healthy enough to work, care for one another, and return home if necessary. Beyond technology, a permanent home also needs a way to organize life as a community. Who makes decisions when power supplies fall, who receives priority access to equipment, and how the group resolves disagreements must all be established before a crisis occurs. In a small team, Authority cannot depend only on rank when someone with more relevant expertise is standing nearby. The rules must be clear enough to create order, yet flexible enough to adapt to situations no one has encountered before. As the population grows, the base is no longer simply a crew and begins to take on the characteristics of a community. Some people will operate machinery, provide medical care, grow crops, manage supplies, and study the surrounding environment. Some may remain only for a short time, while others stay for many years. Shared life will then require private spaces, gathering places, and activities that serve more than the mission alone. A home is not simply a place with enough oxygen and a suitable temperature. It is also somewhere a person can rest without constantly feeling as though they are still on duty. A meal may be prepared for a birthday rather than only to meet a nutritional schedule, while the garden may be tended partly for its beauty rather than solely for the number of grams harvested. When ordinary life begins to exist alongside the mission, the base starts to move beyond its role as a survival machine. Near the moon's south pole, NASA is interested in developing capabilities such as power generation and storage, communication, robotics, dust mitigation, and the use of local resources. The region contains locations that receive sunlight for extended periods, along with cold, shadowed areas that may hold water ice. The moon's proximity to Earth makes it a suitable place to test these systems before sending them to Mars. A failure there would still be serious, but the distance for support is far shorter. The moon could become a testing ground on the scale of an entire world. Humans could learn how to build habitats, operate power systems through extreme cycles, and extract materials in an environment filled with abrasive dust. Robots could prepare landing pads, construct roads, or cover habitats with regolith before the crew arrives. Whatever proves reliable, there may reduce some of the risks when humans eventually travel to Mars. But the moon and Mars are not the same. The moon has weaker gravity, almost no atmosphere, and extremely long cycles of daylight and darkness. Mars has a thin atmosphere, weather, seasons, and far greater communication delays. A technology that succeeds on the moon will not automatically be suitable for Mars. What matters more is that humans learn how to test systems, discover weaknesses, and improve their designs in environments without Earth's natural protection. That is also the true value of simulated missions in Houston. They cannot reproduce lunar or Martian gravity, expose participants to deep space radiation, or create the genuine danger of vacuum beyond the door. In a serious situation, the mission can be stopped, and help remains close by. Simulation results therefore cannot prove that humans are ready to live on another world, but simulations can reveal weaknesses before they become dangerous. They can show which schedules are too demanding, which areas provide too little privacy, and which repairs are difficult to perform in confined spaces. They allow researchers to observe how people use water, respond when equipment fails, and coordinate during communication delays. A flaw discovered in Houston can be corrected through a design change instead of appearing for the first time on Mars. These experiments also remind us that good technology is not merely technology that works when it is first installed. It must continue operating after thousands of days, when dust has accumulated, materials have aged, and the people using it are tired. It must be understandable to newcomers, repairable with available tools, and flexible enough to be used in ways its designers did not anticipate. A settlement survives through its ability to adapt, not because everything always goes according to plan. Imagine the base after many years of operation. Its outer walls carry traces of dust and past repairs, while some original equipment has been replaced with parts manufactured on site. The garden is not large, but it remains green. Water continues cycling through the filtration system, and newcomers have learned to operate the habitat from those who arrived before them. The place is not perfect, but it can recover after something goes wrong. One morning, a pump begins making an unfamiliar sound. The crew does not panic, nor do they immediately wait for Earth to guide them through every step. They redirect the water through a backup system, remove the worn component, and install a replacement stored in the supply area. A few hours later, the pump returns to its steady rhythm, the growing area continues receiving water, and life inside the habitat carries on without interruption. That moment is not as dramatic as a rocket launch or the first human footprint on a new world. Millions of people are not watching, and no flag is planted in the ground. Yet ordinary repairs like this are what prove that humans are learning how to remain. A place becomes a home when life does not end simply because one component has grown old. True settlement is also revealed by the ability to continue after the first residents have left. A procedure cannot exist only in one engineer's memory, and the planting schedule cannot be understood by only one person. Knowledge must be documented, taught, and improved over time. A community cannot depend forever on its founders, just as a city on Earth cannot stop functioning after the generation that first built it is gone. Perhaps the first settlements beyond Earth will not resemble the enormous domed cities of our imagination. They may consist of only a few sealed rooms, a storage area, a growing chamber, and pipes running behind thick walls. Outside will be robots, solar panels, landing pads, and short roads connecting different work areas. Their small scale does not make the dream any less extraordinary, because every square meter must replace some function that Earth normally performs. Inside, a room filled with air, a water tank that has not run dry, and a filter repaired at the right moment are already enough to create something remarkable. Leaves continue to unfold, a meal is shared, and people remain capable of trusting one another after months of isolation. No single element turns the base into a home. That feeling emerges when every system and every person works together to keep life moving forward. Reaching the moon or Mars proves that humans can cross the distance. Surviving inside a habitat proves that we can build a small layer of protection between the body and a deadly environment. But settlement demands something more difficult: the ability to preserve that protection over time, repair it when it fails, and pass the knowledge of how it works to those who come later. That is when a mission begins to become a community. The question is therefore no longer simply whether 4 people can endure a year inside a sealed room. The real question is whether the small human-made environment around them can continue functioning as supplies decline, equipment ages, and Earth is no longer close enough to send help at the right moment. A settlement survives only when the answer is found not in the next delivery, but in the abilities of the people already living inside. Beyond the window, the barren surface remains unchanged. Inside the habitat, however, water continues to flow, filters continue cleaning the air, and a new leaf has just unfolded beneath the lights. One crew member begins a work shift, another checks the remaining supplies, and the ventilation fans continue humming steadily behind the wall. Perhaps this is the most honest image of humanity's first home beyond Earth. Not a brightly illuminated city, but a small house that has learned how to keep breathing. After a year, the door to the simulated habitat finally opens. Air from outside flows into the corridor, carrying sounds that have been absent for months. The participants step across the threshold and see natural light and the wide expanse of sky above them. Things that once seemed entirely ordinary suddenly become vivid, as though they are encountering Earth for the first time. A breeze passes across their skin without traveling through a ventilation system. The scent of plants fills the air, and the sound of running water no longer brings thoughts of storage tanks or filters. They can walk without checking the pressure, the oxygen supply, or the remaining capacity of a protective suit. Only a few steps are enough to remind them how quietly and completely Earth has always protected human life. The simulated mission did not carry them to the moon or Mars. Beyond the walls was still the city of Houston. Gravity still held everything to the floor, and help always remained close enough to reach them. Yet within that sealed environment, the problems of the future were brought into the present, where they could be observed before appearing during a mission with no rapid way out. Researchers can study how a group uses water, protects its sleep, and works together when equipment malfunctions. They can identify the moment monotony begins to weaken motivation, observe how a small disagreement grows inside a confined space, and determine whether systems maintaining air, temperature, and water can continue operating reliably for hundreds of days. Every problem discovered in Houston is one that can still be corrected while there is time. A filter that is difficult to replace can be redesigned, an exhausting work schedule can be adjusted, and an area offering too little privacy can be arranged differently. These changes may appear minor, but on the moon or Mars, they could determine whether a habitat continues operating or is forced to shut down. Even so, a year-long simulation cannot prove that humanity is fully prepared to settle beyond Earth. The participants have not lived in low gravity, endured deep space radiation, or looked back at Earth as a distant point of light they cannot immediately return to. The door can still be opened during a serious emergency, while at a real base, help may be days or months away. The Moon remains an almost airless world where temperatures change dramatically and sharp dust can work its way into every joint. Mars still lies at the end of a long journey, with an atmosphere too thin to breathe and communication delays long enough to force people to manage most emergencies on their own. Those difficulties do not disappear simply because an experiment on Earth has succeeded. Yet every day inside the simulated habitat provides a small part of the answer to a much larger question. It shows that people can learn to use resources more carefully, live together within limited space, and keep machinery operating after the excitement of the mission has faded. It also reveals that seemingly minor details, from getting enough sleep to the placement of a table, can influence the sustainability of the entire mission. Humanity cannot carry the whole Earth with us. We cannot place its oceans, atmosphere, magnetic field, or vast natural cycles aboard a spacecraft. What we can do is recreate a few of the planet's essential functions within a very small space, enough to keep air from escaping, water from disappearing, and temperature within the limits the human body can endure. But even the finest systems will not be enough if the people inside can no longer work together. A habitat remains alive only when someone notices that a pump sounds different, replaces a filter at the right time, or tells the rest of the crew that they are too tired to continue safely. Trust, shared responsibility, and a willingness to support one another are just as important as electricity or stored water. Perhaps the first settlements beyond Earth will not resemble brightly illuminated cities beneath enormous domes. They may consist of only a few sealed rooms lying within a dark landscape, covered with rock and soil for protection from radiation. Inside may be a small water reserve, a backup power system, several trays of green plants, and people who have learned to live without wasting any resource. Every breath inside those rooms will pass through a filter. Every drop of water may once have been in a drinking glass, become moisture in the air, and returned through several stages of purification. A young leaf will survive beneath artificial light, while the steady hum of the ventilation fans will be more than background noise. It will be a sign that the small home within a lifeless world is still breathing. When the door of the simulated habitat opens, the participants return to a planet that does not require them to think about every breath. But perhaps they will never again see a glass of water, a falling rainstorm, or a blue sky in quite the same way. These are not accidental details of life, but the result of a world that has sustained living things for billions of years. When people look toward the Moon or the small red point of Mars, the dream of living beyond Earth may no longer be only a story about rockets and first footsteps. It becomes a story about keeping air inside a room, preserving the green of a small garden, and maintaining trust among people after many years away from home. Because the dream of building a home on another world does not truly begin with creating a new planet. It begins with understanding more deeply every small thing Earth is quietly doing to keep us alive at this very moment.